time. So feel free to ask your question in the chat, and then the speaker will be able to answer you afterward. So let's start by the first speaker. So this is Longley, and he will speak about modeling under location uncertainty in mesoscale dynamics. So take the floor, Long.
Can you see my slide, my screen?
Yes, yes.
Okay. Okay, so good morning. Thank you for coming here. And so what I would like to present today is application of the location uncertainty in mesoscale dynamics, and in particular under the Gadi Giosophic regime. And in these studies, we have incorporated some statistical properties of the high resolution data into our stochastic model. And there are many joint works with Bertrand, Bruno, Noé, et Etienne. So I will start from this plan. In the first place, I will review the LU model very quickly, and then I will present the application to the ocean Tqg model, which corresponds to the last part of my PhD work. And if I have some time, I will also talk about the application to the ERC coupling, but this is only a starting work. Okay. So as a benchmark, I also include the deterministic case in the following. In this setting, the evolution of the fluid particles are driven by this ODE, where U is a vector velocity field. It could be two-dimensional or three-dimensional. While in the stochastic setting, we add some noise to present the location uncertainty and to model the unresolved flow component. And the noise is built from spectral manipulation, in which the WT are the independent standard Brownian motions with respect to probability space with the probability measure P, and X are the orthogonal eigenfunctions of the covariance operator. And then in our case, the evolution of the particles is described by a stochastic differential equation in idle form. However, to simplify the explanation later, I will convert it into Stochanovich form. So as a result, a detrending term will be included into the resolved drift. And this correction drift is described by the direction of the eigenfunctions by themselves. And I will denote this a effective drift as U star. So the evolution of a tracer transported under a deterministic flow is given by the material derivative. Now for a random tracer transported under the stochastic flow is given by the idle formula. And in particular, under Stochanovich form, the classical change rules are quite similar. As a result, data is directed by the total flow, including the noise and the correction drift. Then I will talk a little bit of a reweighting of Brownian motions. So let us first create a new Brownian motion by adding a mean mu t. We know that under the probability measure P, WT is central, but the new WT is not. However, the Giosophic theorem tells us under some conditions, it is possible to have a probability measure Q such that the new WT is standard Brownian motion under Q. And why I talk about this, it is because we could adjust a negative drift into our stochastic flow, and we then convert this idle form under Q into a Stochanovich form, and then adjust the stochastic transport under Q. And in many applications, this negative drift is adopted, such as in the Black-Scholes market model. And I will also explain this later in our application. So now for the ocean Qg dynamics. So maybe many of you knows about the Qg equations. This is basically based on a material derivative of the potential vorticity, together with some forcing and damping term on the right-hand side. There is an elliptic relation between the stream function and the vorticity. And the Giosophic velocity in this case is just given by the perp gradient of the stream function. But in our case, we have used a little bit particle model that's called the Gadi Giosophic Carbon model from Hogg. And their original idea is to build a coupled model in which they could include mixed layers in both components to describe the exchange of momentum and heat. So in that case, we could keep evolution of the mixed layer temperature, and by the convection, the heat convection, and the Ekman bumping of the temperature, there will be a vertical increment into the interface. So this is why there also a forcing term applied on the vorticity by the variation of temperature. So now I will show first of all the determinate simulations by different resolutions. So on the left-hand side is the reference from the eddy resolving simulation of 5 kilometers. In the middle is 40 kilometers, and on the right-hand side is 80 kilometers. So there is an important parameter in this configuration is Bartolini-Rossby deformation eddies, and the maximum of this deformation is 40 kilometers. And there we know that if the horizontal resolution is under or close to the deformation radius, then we could not solve the eddies in the simulation. And this is why in the coarse determinate simulations, we won't see the effect of the eddies, so mainly the eastward jet and their recirculation flow. So then our motivation is to can we using the stochastic formulation to reproduce the high resolution simulation at some level. So now I will introduce the stochastic Tqg model. And for the evolution of the temperature, it's just a 2D transport, stochastic transport of this temperature. But for the evolution of the potential vorticity, there will be some source term from the derivation of our model. So where did this term come from? So this is a Jacobi operator apply on each component of velocity. So when we apply a curl of the acceleration term with two different velocities, we always have these terms. This is zero only when these two velocities are collinear. And also that in our derivation, we're using the classical scaling analysis, so such that these two terms are at the same order of velocity. So we cannot neglect one and keep another one. But keeping these terms, we have shown that the total energy of the flow is conserved. So now I will talk about numerically calibration of the UF for the noise and the correction drift. And you might see that it's quite similar to that we talked yesterday. So with a given set of eddy resolving stream function, P, I denoted as small l for the fine grid. So the first thing we do a spatially high pass filtering of the data for the coarse grid points. So what we get is a local fluctuation that we denoted C prime. And then we derive the Giosophic velocity by applying the perp gradient on the cross grid. And then we do a detrending of this signal by removing the time average, and then perform the proper orthogonal degradation such that the original fluctuations are decomposed into a set of temporal mode and spatial mode. And the spatial mode is orthonormal, and the temporal mode are orthogonal. So we then do a rescaling of the UF by including the square root of the eigenvalues into the spatial mode and times a time scale. And this time scale is a small scale correlation time. Usually we choose the cross resolution simulation time step. And then the last thing we do is we recover the time average of the local fluctuations. So that's corresponding to the negative drift that I talked before. And this term describes the time memory of the eddy effect. So basically, we can find the coefficient of this Gaussian drift by just project this different term into each mode that we are selected. So here are the simulations from different models. So what I focus on is on the right-hand side, is using the stochastic simulation and including the statistics from the data. It is at 80 kilometers, and what we can see that it starts to reproduce the eastward jet and the recirculations. But maybe due to the noise too strong, and its increase and the variability in the year that not presented from the high resolution. Then we do a analysis of all these results, so we can look at the long-term average using 100 years data. So this is the time average of the upper layer spin function for different models, and we can clearly see that the reproduction of the jet region. And now I will talk a little bit about the vertical effect of the noise structure. So what I do here is to using another two different noise. So the first one is before we learn the UF, we do a vertical integration of the local fluctuations, and then calibrate the UF. And in that case, I will have a topic noise. And on the other hand, we can do inverse. We remove the vertical average of the fluctuation, but we only keep the vertical fluctuation, and in that case, we only have clinic modes. And then we reperform the simulations, and we look at the prediction of the statistics. And this time, what we are focused on is the bottom layer spin functions. And what you can see here is that neither about topic or balconic noise I can reproduce the result of the reference. They produce the wrong sign of the reference. So this meaning that both barotopic and balconic modes are important in the vertical structure of our noise. So we in my thesis we also propose a dynamical optimization to update the noise in time by project the noise onto the isosurface of stratification. So that basically means that we only want to act the noise on the float volticity, but not on the stratification. And in that case, you will see on the right-hand side, there are much more variabilities everywhere. And then we analyze these variabilities by checking different metrics. There are some people propose to look at the dispersion and the pattern correlations. So basically, this compare the standard deviation of cross model and the standard deviation of the reference model. So from the definition of dispersion, it just tells us that if a cross resolution model predict well the variability to the reference, then this dispersion should be quite small. But inversely, it should have a high correlation. And apart from that, we also diagnostic the eddy kinetic budget by splitting the velocity into a temporal low-pass filtering component and the residue component, and splitting the energy into standing component and transient component. So we perform these metrics for different resolution as 40, 80 kilometer and 120 kilometers, and compare these three models. And the final conclusion is that so the results are not so sensible to the resolution, and the dynamic of the noise is also important. So now I will talk about the application to the ERC coupling. As I said before, it's just starting work in my postdoc. So we still use the formulation from the Tqg model, QGCM model. So the key point in the coupling is the model of the stress. So in this case, they are proving from a paper that the wind stress is proportional to the difference between the wind and the current. But here the coefficient drag is a constant. And then the current stress is proportional to the ratio of the density between atmosphere and ocean. We also have a momentum equation in the Ekman layer by including a vertical derivative of the stress. So we apply this in our stochastic formulations. So we have two first ideas. So the first one is to keep the Ekman layer momentum equation and keep the resolved component of the stress. So as a result, the noise in the mixed layer will satisfy the Giosophic balance. On the other hand, we add additional additive random stress into the Ekman layer momentum equation. And in that case, the mixed layer noise would be Giosophic by this vertical derivative of the random stress. But the question that we have is we don't know how to model this random stress. So the first idea that we do is to follow the determinist formulation and adapt it for the noise component. So these are the first results that we have using these two different formulations. So on the top is the time range of the upper layer strain function, and on the bottom is time range of the sea surface temperature. And on the first column is the high resolution reference, and the second column is determinist low resolution model. The third column is the LU model under the Giosophic mixed layer noise. And the last one is on the Giosophic noise. So there is a thing that we didn't understand is when we add this random stress, so also adding random Ekman bouncings, the results reduce the eddies. So they destroy the jet in this case. And we haven't understand why this happens compared to the Giosophic noise. So for this, we are thinking about to look at the current feedback from these two reference papers. Basically, they say that if we coupled in the stress, if we coupled wind with the current, then the current will have a feedback, which plays eddy killing effect. So I perform this analysis for the high resolution data, and we observe that in the active region in the ocean, there really a negative work to reduce the kinetic energy in the ocean. So what we are wondering is that if in the Giosophic noise regime, since we have a additional term, is this term allows to reduce a lot of eddy energy in this active region or not. So that's the following work. So for future works, we would like to calibrate the dynamics of the UF using some advanced data analysis techniques, but it is still difficult because to preserve the orthogonality in time of the UF is still not clear. And we would like also to take account of the relative velocity into the Ekman layer momentum. We also want to extend the uniform drag coefficient to a spatially dependent version, meaning that it depends on the wind, on the current, and also the variation between of the temperature in ocean and atmosphere. And we also want to include the adjustment of the wind forcing with the temperature variations. And finally, I also have a strong interest in to combine the stochastic Tqg model and the stochastic surface Gadi model, which correspond to works that I did in my PhD work. So there is a very nice paper from Guillaume Labai that may be interesting for us. So that's all for today, and thank you for listening.
Thank you, Long. So we have little time for one or two questions, if there is any. So meanwhile, you could stop sharing, and then the next speaker could. Evgeny, maybe you could start sharing your screen. So if there isn't any question, okay, so we can continue. But in any case, feel free to ask questions in the chat. So Long will answer to them.
Okay.
Okay. So the next speaker, Evgeny Dinvey, and so we will talk about stochastic surface wave. So you have problem to share your?
Yes, yes. Just a bit. I can't find the. Oui. I'm sorry. Just.
It's at the bottom of the.
No, I found the bottom, but. Okay. Yeah, it asked me of some preferences. I don't understand. Okay. Just a minute. Das das me to.
Maybe it's better to switch the presentation of Laura and yours. What do you think?
It doesn't work? No? No.
No.
You cannot see my screen. No?
No.
No. Can you show? Is it just the small arrow here? No? Okay.
Yeah, you are here.
No, it's desktop.
Yeah. Okay. Okay, desktop 1. This should work.
No, but still it asks me.
Yeah, and then open this. Go there. Preference. Okay, yes. Yeah, maybe you can switch and we.
Yeah. Okay.
Yeah. Okay. Laura, are you ready to present your presentation? Laura is not there. Yeah. So Evgeny. Maybe you could use the Lung's computer. I don't know.
Laura is there.
Laura. So Laura, could you share your screen and switch with Evgeny?
Sure. Just give me a moment just to get the presentation up.
Okay. Okay, great.
Okay, can you see my slide? Can you see the right slide here?
Yes, no problem. Go on. Thank you.
Okay, so hi, I'm Laura Cope, and today I'm going to talk about some results that I've obtained over the last few months. I've been working with Darrell Home, looking at the effects of buoyancy gradients on the formation and maintenance of zonal jets. Before I begin, it's worth clarifying what I mean by the term zonal jets. So zonal jets are strong currents in fluids that flow in the east-west or the zonal direction. And the image at the bottom of this slide shows the atmosphere of Jupiter, and the alternating pattern of currents that you can see are called zonal jets or jet streams. So zonal jets naturally exist in a variety of geophysical fluids, both on Earth and other planets in the solar system. So, for example, they've been observed in the atmospheres of Jupiter and Saturn. And on Earth, we have, for example, the mid-latitude jet streams in the Earth's atmosphere. And there are multiple jets in the Antarctic circumpolar currents in the Earth's oceans. Now, the mid-latitude jet streams in the Earth's atmosphere play a key role in the climate system. And so understanding their properties is of central importance in our quest to understand the climate. And so this leads me to the main question that I've been trying to answer in this research, which is, what insight using idealized models, and in particular, the role of buoyancy gradients? Now, I'm going to begin this talk by initially neglecting buoyancy, and I'm going to talk about one of the simplest systems that permits the spontaneous formation of zonal jets. And this is called the quasi-geostrophic, or the Tqg model. And as a brief overview, we're going to consider a single two-dimensional layer of fluid that's doubly periodic in both the zonal X and latitudinal Y directions. And in addition, we're going to use the beta plane tangent plane approximation. And we're going to apply a stochastic body force as an idealization of small scale turbulence, because there are no instabilities in this system that would otherwise be a generation mechanism for a source of small scale eddies. Now, the entire dynamics within this system can be described by a single dynamical variable, notably the stream function, psi, or the potential vorticity, q. And the governing equations of motion are shown in the center of the slide here. So within the Qg vorticity equation, we have on the right-hand side a stochastic force, and we're going to incorporate linear friction in order that the system can reach an equilibrium energy state. And we're also going to use hyperviscosity for numerical stability. And the relationship between the potential vorticity and the stream function is shown here. So where f here, this is the Coriolis parameter. And since we're going to be considering a doubly periodic beta plane for simplicity, f is shown at the bottom here. So in this case, the background potential vorticity distribution is going to vary linearly with latitude y. And finally, just a brief note about the stochastic forcing that I'm using. It's approximately white noise in time, and I'm forcing the system both isotropically and homogeneously with a well-defined wave number or spatial scale that is small relative to the size of the domain. So I'm forcing a narrow annulus of wave vectors in Fourier space. And this is an example distribution in physical space here. Okay, so I'm going to show you a video now from an example numerical simulation from this Tqg model to demonstrate that it does indeed lead to the spontaneous formation and maintenance of zonal jets, even when the jets are not present in the initial conditions. That's because this system contains the key ingredients that are essential for the formation and maintenance of jets. And these are planetary rotation, turbulence, and friction. Okay, so we're going to start with a velocity field that is initially at rest, and we continuously force the fluid at small scales. And as you can see, some larger scale coherent structures are emerging. Now, the yellow fluid is flowing to the east and the blue to the west. And over time, these structures are becoming elongated in the zonal or the east-west direction. Now, at this point in the simulation, we can see the emergence of a yellow eastward jet here, two yellow eastward jets here, and two blue westward flows. And shortly, these two jets are going to merge to form a single jet. And so in this particular simulation, the system will equilibrate with two yellow eastward jets and two blue westward flows. So this is a solution to the QG system. And before I continue, it's helpful to introduce the concept of Hov-Molar plots or latitude time plots as a convenient method of illustrating the solutions from the numerical simulations, rather than playing, for example, two-dimensional videos. So let's consider an example on this slide, where once again, we're going to start with the velocity field that is initially at rest. Now on the left-hand side, you can see snapshots in time of the zonal or the east-west velocity field. And if we take the zonal average of the plots on the left, then we obtain the plots in the center of the slide here. And these show the zonal mean zonal velocity field. And if we compute this velocity field or this profile at each instance in time, then we can generate latitude time plots, such as the one shown on the right-hand side of the slide. And in this particular simulation, you can see that a single yellow eastward jet has formed, and it's just randomly wandering throughout the domain. I'm going to be showing a few examples of these latitude time plots throughout this talk, and I want to emphasize that time will always be evolving along the horizontal axis. Okay, so that was the QG model. Now let's consider what happens to these jets when we incorporate the effects of buoyancy and buoyancy gradients. And a convenient system for doing this, and which falls under the remit of the STUOD project, is the thermal quasi-geostrophic, or the Tqg model. And in this system, we're going to introduce two new fields. So these are the buoyancy field, which I'm showing in red, this is the B, and a bathymetry field, H, in blue. And the Tqg equations are presented in the center of this slide, where once again, and for consistency, we're going to incorporate a stochastic body force, linear friction, and hyperviscosity. And as before, the relationship between the potential vorticity and the stream function is given here. And we're going to be considering doubly periodic beta planes. So the Coriolis parameter is given by this expression here. So what we're going to do is as follows. We're going to run a QG simulation for a fixed period of time until the system has reached an equilibrium state and the zonal jets have established themselves robustly within the velocity fields. And in particular, we're going to consider parameters such that 3 zonal jets emerge, as shown here. Then we're going to use the stream function at the end of this simulation that contains 3 jets as the initial condition for a Tqg simulation, where we're then going to incorporate buoyancy gradients. Now, to begin with, we're first of all going to introduce buoyancy gradients without a bathymetry field. So we're going to consider an initial buoyancy field that varies spatially in the zonal x coordinate and has amplitude A. And we're going to consider different amplitudes A, and we're going to keep all of the remaining parameters constant. Okay, so let's take a look at some results. On this slide, we're considering 5 different amplitudes A of the initial buoyancy field. And as you can see, in all cases, the zonal jets that emerge in the Tqg equations on the left-hand side of the simulations persist and are maintained in the Tqg simulations. And in fact, this result has been tested and is robust across a wide range of different parameters. So we can conclude that zonal jets are maintained in the presence of horizontal buoyancy gradients. Next, we're going to add some bathymetry into the mix. So this time, we're going to repeat the experiments that I've just described, and we're going to be running a QG simulation to spin up a solution with 3 zonal jets. And then we're going to use this as the initial condition within a Tqg simulation. However, this time, in addition to an initial buoyancy field, we're also going to incorporate a spatially varying bathymetry field, given here, that is small scale and varies in both the x and the y coordinates. And once again, we're going to run a series of experiments where we vary the amplitudes A of the initial buoyancy and bathymetry fields. This time, the results are presented on this slide, where we do observe some differences. So, as the amplitudes of the buoyancy gradients and the bathymetry field increase, we note that there is a transition in the system where the jets stop being maintained and are instead suppressed. And this is an interesting result. And we observe that for sufficiently weak buoyancy effects, the jets are unaffected. However, as the system, as the buoyancy gradients of the bathymetry become sufficiently strong, the jets become suppressed. So just to conclude, we've been using idealized models to study the effects of buoyancy on the maintenance of zonal jets. And we began by introducing the Tqg model, which is well known to produce solutions that can contain robust zonal jets via the inverse energy cascade. We then considered the Tqg model that introduces the effects of buoyancy gradients and bathymetry in an idealized format. And in this system, we observed a transition where we noted that for sufficiently strong buoyancy effects, the jets become suppressed. So to conclude, horizontal buoyancy gradients and bathymetry remove entropy conservation, which in turn removes the inverse energy cascade. And this prevents the formation of large-scale coherent structures, such as zonal jets. And the strength of these buoyancy gradients are clearly an important consideration. And so the question remains as to how do you define the transition between the maintenance and the suppression of jets as the buoyancy gradients increase in magnitude. And I'm going to stop my talk here, and I'll be really happy to answer any questions that you may have.
Thank you, Laura. So, is there any questions in the assistance? So, yeah, no question. So feel free again to ask questions in the chat, and Laura will be happy to answer to them. So we can move now to the talk of Evgeny. So Evgeny, are you ready to share your talk?
This one, yes.
Okay, this one.
But no, this share screen.
Okay.
Right, we see.
Can you see my screen?
Yes.
Super. And can you see the next? Oh, wait. Okay. Okay. Can you see the next page?
Yes, it's working.
Ah, super. And you can hear me.
Yes, perfectly.
Super. Okay. Now let's start them. So yeah, the title, you can see it. I'm working on basically in water wave theory. What is water wave theory? I'm interested in waves that you can see in the ocean. So I mean, and the ocean for me is like first of all 2-dimensional. Well, okay. We can do it 3-dimensional as well. but just for presentation, let it be two-dimensional. And it has a flat bottom. Yeah, it's a normal suggestion. So even Businesks thought that, I mean, it's normal, so it's okay. And yeah, so waves normally look like this, as you can see on the picture. Okay, not all of them, but some of them look like this. So I'm especially interested in localized ones like tsunamis. Function eta represents the form of the wave and so on. Okay, so the main assumption. So I'm working with the TM. So for me, yeah, I want to include stochasticity in the water wave equations. And how we usually do it, we use this principle of location uncertainty, so that basically the speed can be divided into components like smooth component, more classical deterministic one, yeah, and the component that contains all the noise or uncertainty and whatever. Okay, and what we suppose, first of all, we suppose that the velocity is divergence free. So both components, stochastic and the smooth one. And we do a normal assumption that usually is done in water wave theory, that the flow is potential. I mean, the potential is the coarse component of velocity, so the smooth component. So, and all vorticities, they are part of the noise. Okay, but the main picture is potential. Okay, and at the bottom we have a normal condition. So a Neumann kind of condition, so that the fluid at the bottom is just sleeps, yeah, and cannot go up. Okay, yeah, we can introduce covariation matrix. It's covariance of the noise, and so what do we have? What kind of conditions we have? First of all, kinematical boundary condition. It's a condition basically that's saying that the surface moves together with the fluid. Yeah, it's clear. Yeah, so the fluid particles, they're moving together with the surface. This is what the kinematical condition basically is about. Okay, I mean, it looks a bit maybe not super familiar, but I mean, most of the terms, they come from stochasticity, yeah? So this part, I mean, it should be familiar. Okay, so this is a boundary condition, and we have a moment equation, yeah? So yeah, again, most terms here come from stochasticity, and yeah, this term basically is familiar to everybody. Okay. And yeah, I just remind you that we consider U to be potential, the velocity, the smooth part of velocity to be potential. Okay, and what do we want to do? We want to reduce this dynamical equation to the surface. Okay, so how we are going to do it? Actually, we are going to proceed very similar to what people usually do in the classical theory. Okay, so first we introduce the trace of the potential. Okay, so basically function capital phi is it's a trace of our function phi. Okay, and so what do we have? We know that the flow is potential, so the main flow is potential. We have the Neumann boundary condition on the bottom, and we have now we have a Dirichlet boundary condition at the surface. So with such an elliptic problem, we can always associate some the so-called Dirichlet to Neumann operator. I mean, that's actually a classical definition. Okay, so and okay, well, what is the main point of this operator? If you write down the kinematical boundary condition, you will see that it actually, I mean, if you remove all the stochastic part, so basically the derivative of surface elevation is defined by this operator. Yeah. So okay. Okay. If you want to reduce a second equation, dynamical equation to the surface, we need to represent derivatives in terms of this function phi, capital Phi. And so we have derivatives of the function phi. Yeah, so this function is defined on the real line already. And so g phi is also defined in the real line. Okay. So we can actually represent the gradient phi in the terms of functions that are defined in the real line already. So we're actually reducing the amount of dimensions. Yeah. So we work with this 2D problem. Now we basically reduce it to 1D problem. Yeah, but we will need to find the second order derivatives, third order derivatives. They're a bit expressions are big, but it's basically the same technique. So we basically differentiate and simple calculus. I will not write them down. Okay. And yes, and you can reduce the dynamical equation to the boundary, and that's what you will get. I actually did not write it completely because it doesn't fit to this slide. So question doesn't fit to this slide. So yeah, it's I think it's okay. Just see those here. Okay, but the main thing what we can see in these brackets, the first line actually it's a very classical equation that we actually saw in the water wave problems already many times. Okay. People from the community of the water waves, for them they remember this equation by heart. Okay. The only thing that they write it in terms of phi, not derivative of phi. But I mean, in the deterministic theory, you can just remove derivative from here and from here. But now we have a problem, is we cannot just remove derivative from here and here. So a bit of too many derivatives. But it's okay, still doable to work with. But yeah, obviously this equation is not super fun to work with. So maybe we need a bit more different approach. And let's discuss this. So in the classical theory, we know that actually water wave equation can be represented in the Hamiltonian form. Actually, those two equations that I showed you, the deterministic analog can be represented in this form, in this nice form. So actually, this variational derivative is basically this one. Yeah, it's what you see in this bracket. Okay, where H is actually the total energy, yeah, so potential energy and kinematic energy. Okay, and yeah, you saw that we cannot just remove the derivative, so we will need to work in this variable. So maybe we can use the notation for this one, or just introduce a velocity variable. It's not exactly a velocity of particles. I mean, it's just derivative of potential precisely. But I mean the dimension. So basically, like some kind of velocity. Okay, and so now let's do a bit differently. So now I want actually to include the noise via this Hamiltonian formulation. There is an obvious advantage of it. So energy H will be a conserved quantity, and maybe this the final equations will look nicer. So, but I still want to be consistent with the first approach. Yeah. So maybe I should do some simplification that actually this part coincides with that ugly, or not maybe ugly, but very huge equations. So I actually want to find apparatus GI so that two formulations are consistent, at least at some approximation. Okay. Since our previous two equations, kinematical boundary condition, dynamical boundary conditions, were written in the eta form, so we actually have to rewrite this Hamiltonian formulation in the eta form as well. So I mean, but it's not a big problem. We can do it. And so yeah, we want, and we already saw that actually the first part that comes from the deterministic theory, it already coincides. We don't have to find this separated G. We already know it. Okay, so we actually want to model the noise in the way that this equation coincides with the equation that we saw in the previous slides. Okay, so first, if you remember, we suppose that the noise is divergent free, so I mean it's natural to represent it in this form. And also, since I reduce it to the surface, it's also natural to suppose that okay, we have functions here that is a composition of eta. Eta is a surface elevation. Okay. As you can see, the noise actually depends on eta, yeah, on one variable. It does not depend on velocity, so it's clear that we cannot really make equations the same from the two different approaches unless we actually do approximation. And so let's linearize the gradient of Hamiltonian, but we linearize it only in the noisy part. So we don't have to touch deterministic part. Okay, and yeah, in the water wave theory, people really know how to work with the Dirichlet-Neumann operator. We have some expansions of it, and actually, to calculate what is the operator for flat surface, it's a very simple problem. Any student can do it actually, and get that expression. Okay, so and if we do some linearization of the noise, and we remember that the noise we represent it as stream functions. So yeah, basically what I'm doing the Taylor expansion here, nothing else. And yes, so to make this antisymmetric, yeah, so we have the antisymmetric operators. To make it antisymmetric, I need to suppose that J1, 2 is 0, and so it leads to the fact that J21 is 0 as well. Okay, and yes, and I need to admit two conditions on my stream functions phi I, that I really have an antisymmetric operator. So you see, I have derivative, and you do integration by parts, you have minus, so everything's fine. So really, I mean, it fits. So, but yeah, I have to admit this for my stream function. Okay, I can do the same with the second equation. Basically the same. And so at the end of the day, I will get my antisymmetric operators that I have in the Hamiltonian formulation. And it looks like this. And yes, they're antisymmetric because derivative, and you integrate by parts, we will have minus, so everything's fine. Okay. And yes, it's not supposed to look exactly as operator J. It comes from the deterministic case. Okay. What we can also notice that we actually can come back to the initial variables at and phi. So we can actually, if we change variables, we change the form of our operators, antisymmetric operators, and but it can be calculated. And yeah, it turns out actually that this guy is actually well defined. So we actually can formulate in the original variables at phi. I think it's a kind of advantage that may help to study analytically this actually Euler equation on the surface, but already with stochastic terms. Okay. What else? Just a couple of words on the noise model. Okay. So if you remember, I suppose divergence free of both components of velocities. How we can achieve it? In compressibility condition, and this condition we also have to suppose this one, but it's not really too restrictive. I mean, so if we calculate elements of matrix A, so I mean, and we know that the sum of them should be 0, and so I mean, if we, for example, solve a problem like this, so it already gives us some string functions that are okay. I mean, and one of the possible solutions is this one. And it basically a huge class of stream functions. And even more, so I don't actually have to suppose that they're equal. I actually have to suppose that the sum of the difference is 0. So, it's not too restrictive. Okay. so if we have a Hamiltonian formulation, we can actually do what we call Hamiltonian long wave approximation. So normally, if you see in the ocean, waves are long, and we know this, and it was used to obtain many simplified models. And so first, what we can start with airy waves. So we can just suppose that we have just linear situation. All the waves are that small that I mean, we have linear theory, and then we can just take Hamiltonian, just all the terms that actually gives us linear equations. Yeah, so basically we take Giosophic operator for a strip. Yeah, for a strip. Okay, and yeah, we can calculate. Basically, we can actually find the solution exactly, and how airy did at some point in the past. Yeah, and okay, this fundamental matrix basically represents the airy solution. Yeah, and what we have else, okay, what comes from stochastic part, this actually gives us some shift of solution. Some shift of solution. And yeah, if you look actually closely, what kind of solution that we have? Okay, we are working with linear waves right now. Okay, so it actually gives us the shift in the space variable. So basically, yeah, stochasticity gives nothing new here at this point. It just gives us a shift of solution. So we have at D represents a deterministic solution, deterministic airy waves. Okay, let's go a bit further. Suppose we have linear noise, but non-linear equation. For example, H can represent like fully non-linear Hamiltonian. Okay, still we can actually solve this. We cannot solve this equation, but actually here the noise, if we just have the linear noise, it also gives a shift. And this is already an interesting result. So, for example, if we have a tsunami somewhere, a solitary wave, so we know that somewhere in the ocean solitary wave, and it's going in our direction, and we want to know when it comes. So since we have some uncertainty about concrete data, so it also gives us, okay, it can come a little bit earlier, a little bit later. Okay, so some kind of stability, yeah. Okay, so but as you can see, so if we just regard models with only linear noise, yeah, maybe, I mean, it's interesting. So we'll already have some results, but from the analysis, from the mathematical point of view, maybe it's boring. So we actually already just reduce everything to the deterministic case. So yeah, maybe we should regard some more interesting, like approximate H by some nonlinear terms and use some nonlinear noise. And yeah, we can actually have some family of extensions of classical systems that people regard in water wave theory. Okay, this is one of them. This is one of them. This is actually my favorite toy. I mean, I did my PhD. I concentrate mostly on equation, deterministic equation of this field. Why? Because okay, when I did my PhD, actually people were interested in the fully dispersive quasi-nonlinear equation, and this is actually a stochastic extension. At the end, I will just show you some simulations of this equation, and I need to know how much time is left.
There is no time left normally, okay. But so go quickly and
yeah,
then
I will spend 1 minute. Okay, we can actually produce other models. I mean, in this framework, like for example, ABCD, Buoyancy models, we can extend them, give some stochastic extension. we can we can do we can model some. Okay, we can stochastically extend some unidirectional models like BBM equation. And so, okay, so basically we have all the series. So here I'm just basically talking about how to do numerical simulations of these models. And yeah, I just write in integral form, mild integral form, Riemann integral equation. Yeah, so here I'm just using the fact that I can actually solve the linear problem exactly. Okay, and yeah, some simulations. Okay, maybe I just stop here. Thank you.
Okay, thank you, Evgeny. So is there any questions to Evgeny? So again, you can write them in the chat. Okay, if there isn't any questions, so we have a short break, so we can take a coffee virtually, and then we will have the invited talk of Franco Flandoli after the break. So let's take 5 minutes for the break, if you don't mind, and so maybe to have the presentation of Franco in 5 minutes, let's say 10 minutes, in 10 minutes. Okay, thank you.
Hello, Etienne.
Hello, Sebastian. How do you do?
Oh, good. Yeah, sitting in the sun here.
Yeah, it's sunny in Germany. Yeah.
So it's really nice work you're doing in your group there. I'm really enjoying and seeing that.
Oh, thank you very much, Sebastian.
So I was actually wondering if we can get you to visit us in Potsdam at some point. I mean, I think there's some interesting
That would be a
things we
great
could
pleasure.
discuss on sort of parameterizations and data assimilation and things.
Yeah, I would be very happy to come to visit you. That would be great.
So,
Yeah. Okay, we can arrange that. No problem.
yeah. We should well, maybe wait a few more weeks.
Okay.
But,
Yeah.
maybe in the spring or some good time. I mean, where it's
Okay, perfect. So we can start now. We are very pleased to welcome Franco Flandoli as a new member of the advisory board of STUOD. So he will give a talk on mixing and dissipation properties of transport noise. Franco, you can take the floor.
Thank you. Thank you very much for the invitation. It's a great pleasure. The talks that I attended are really wonderful. You are doing fantastic work from many viewpoints. My contribution will be mostly on two theoretical sides. One is well-posedness issues, but at the very end of the talk, I will talk about these well-posedness issues. And the other is in the title, mixing and dissipation. The well-posedness will come from the dissipation, so it's related. Maybe not all transport noise has these properties. You will see in the theorems that there are assumptions which try to clarify that sometimes transport noise has strong properties in this direction. And I prepare too many slides and too many informations, but let me only emphasize that Lucio Galeati, PhD in Bonn, is responsible for the first paper in this stream. I mean, restricted to my group or to some people. Certainly there are other contributions in other directions, but he was responsible for the beginning, the idea of this technique. And with Dejun Luo, we continued this together with Lucio, and also other Umberto Paparettera is contributing at another side, which is more related to Wong-Zakai, but is always the same stream of ideas. And which is the point? Transport noise appeared classically in passive in equations for passive scalars or vector fields. Here is the simplest example of a temperature with a transport term, which is mandatory with the velocity field. And since decades, people replace the velocity field, the true velocity field, with the simplified versions like white noise in time or Ornstein-Uhlenbeck in time, and various degrees of covariances, etc., mostly for the investigation of difficult questions about intermittency and so on. For vector fields, for instance, the question of the dynamo of magnetic fields. And for the transport in the equation itself is more critical because there is already a velocity field. And so adding another contribution to the velocity field requires justification, but exactly this is the group that contributed mostly with Daryl Holm and many others to understand this. This is the equation in 2D. 3D is more complicated. We need other terms. And so there are these two models. These are very different. The role is very different in these two models, but some gamma mathematics is parallel in the two. I want to spend some pedagogical slides at the beginning on von Sakai and Stratonovich, very well known, but I think it's important to recall some ideas, and then I will move to mixing, etc. What about von Sakai? Sorry, is really well known, but if you take a deterministic differential equation in finite dimension to simplify, and linear, all linear operators, just to simplify, not because the theory is restricted to linear, but just to simplify the notations. In one of the terms, there is a rapidly fluctuating, at the beginning, deterministic term, but then maybe described by a random process, rapidly fluctuating. If this approaches Brownian motions, if the W approaches Brownian motions, so the time derivative approach white noise, under certain conditions, is well known that in the limit we get a stochastic equation where the interpretation is the Stratonovich one. And let me recall, just for completeness, that Stratonovich calculus is very good because it's similar to the deterministic calculus, but if we want to take expected values, these are terrible for the Stratonovich, so we have to move back to Ito, in which there are cancellations. So in Ito there are cancellations, in Stratonovich they are hidden. There are also there, but they are not hidden. So we need to move to Ito to take advantage of the cancellations due to the independent increments of the Brownian motion, essentially, so to speak. And so there are rules which move Stratonovich to Ito with the correctors. Although this is very, very well known, but the point is that all my talk depends on the correctors. So if we miss the fact that Stratonovich is natural because of von Sakai, for a deterministic person, because for a stochastic person it could be natural for other reasons, and for a fluid dynamics it could be natural because there are conservation laws and so on and so on. But for a deterministic person, it could be strange to see that we use that particular object. This is the natural one from von Sakai, and when we move to Ito in order to take advantage of the cancellation, we get a corrector, and the corrector is the key of all the results I'm going to explain. And when we move to Ito, there is cancellations at several levels. For instance, these two that are well known. Summarizing, if we start with a deterministic equation with rapidly fluctuating coefficients, we end up with the Stratonovich or the Ito, where the corrector is this 1/2 sum of bk squared. What happens, okay, here, this slide, we could jump, but what I want to show, so there is a question from Arnaud, or is a mistake? Arnaud, there was a
mistake, sorry.
Oh, so this slide is to convince deterministic people that the corrector is really there, even if we apply, let's say, applied mathematics computations with approximations. Namely, we start with the equation with the smooth noise, still smooth, not in the limit. We rewrite integrals using increments of the integral on small intervals, replace and replace. So let's jump these lines of computation, but you just replace the equation inside itself 2 times, maybe 3 times if you want to control the remainders. And for instance, end up so that there is the bk, the operator bk that appears in front of the part with the noise. bk is applied to increments of the solution. And when you replace this increment of the solution with the equation again, the bk appears against the bk. And in ordinary calculus, these terms would go to zero because it would be infinitesimal or higher order. But here, these are multiplied by the increments of Brownian motion twice. And the properties of quadratic variation of Brownian motion is such that these multiple increments converge to a finite non-zero in contribution. And so the sum, 1/2 sum of this BK appears spontaneously if you do computations. Well, let's go to PDEs. So first, the case of a passive scalar. Let me mention, this slide is just to remind that there is a huge activity worldwide about mixing, dissipation, and enhancement. These are the two keywords nowadays. Here there is a long list of people. And a little bit more classical, but you can find, for instance, in the book of Maida-Kramer, there is this, the link with parabolic equation with an extra constant in this case is the dissipativity constant, an extra dissipativity, what is called sometimes eddy dissipativity. And these are classical topics, so I want to speak about them in the stochastic case. So when the velocity field that was present, let me go back to the previous slide, there was always a velocity field in the passive scalar equation. The velocity field now is white noise, justified, as I showed before, by Wong-Zakai. It's necessary for the sequel to introduce the covariance Q of the noise, so that the covariance at the stochastic level and then becomes this formula for the coefficients of the noise, because what happens that when we move Stratonovich to Ito, the corrector, which is this 1/2 sum BK square in the finite dimensional case, the corrector becomes a second order differential operator related to the covariance. Precisely, the corrector is this second order differential operator. Since I assume that the vector fields are always divergence free, I use divergence solenoidal vector fields only in the talk. You can rewrite the differential operator in the so-called variational. So variational form, divergence form, and the coefficients are this covariance computed at the same position x on the diagonal. The covariance depends, of course, on two parameters, but you compute on the diagonal, and these are the coefficients of the corrector. This is a key fact. And due to that, we can, so the equation here is rewritten, the equation for the temperature, there is again the Ito and this second order operator. Now we can write a variation of constant formula with this operator. So introduce the semigroup ET to L, this operator L, and have an equation of this kind. Let me stress that the equation is not parabolic. The equation was, sorry, not parabolic. Let me go back to the PDE for the temperature and clean a little bit. The equation contains a parabolic term at the beginning that can be zero. It's in some investigation K is zero. So the equation could be first order PDE of transport type that moves to something which looks parabolic but is not parabolic. In this formulation, there is an Ito term and a corrector, which is a second order differential operator. In the second order differential operator, there could be the K Laplacian at the beginning if there is a K Laplacian. So, okay, so this second order operator could be a Laplacian given at the beginning plus the correction due to the noise, or just the correction due to the noise, depending if you study one case or the other. Of course, if there is already a Laplacian at the beginning, the problem is parabolic. Otherwise, even if this formula looks a parabolic equation, is not a parabolic equation. If we take the expected value, since the Ito term disappear, here the cancellation is fundamental. If we take the expected value, the solution, which becomes deterministic, is solution of a parabolic problem. In both cases that we started from a first order differential equation with noise, or a parabolic problem with noise, in both cases, the expected value satisfies a parabolic problem. But the expected value is not representative of the true solution. Like, we know many problems in which the expected value is 0, but there is a lot of randomness and complicated turbulence features. So, the problem is whether the true solution, stochastic solution, is close to the expected value. So this is the problem. Or if you want, if the variance of the solution is small. So when so the question is when the true solution theta is close to its expected value theta bar. Theta bar solves a parabolic equation, theta solves, depending, we have different cases. And the theorem states an inequality, quantitative inequality, based on quantities related to the covariance of the noise. So the covariance of the noise has two features, sort of upper bound and lower bound that are here. The upper bound is in this particular sense, and the lower bound in this other sense, and these are completely different. So we should not think that they go in contrast one to the other, because they are completely different. The first one, the upper bound, is related to the operator norm. The covariance function builds a covariance operator. The operator norm of this is related to this upper bound. The lower bound is not related to operator norm, because the covariance function is computed along the diagonal. So intuitively speaking, heuristically speaking, is related to the trace. The trace of the operator is the integral of this Q on the diagonal. So one is related to the operator norm, the other to the trace. And of course, we know that there are operators that have infinite trace, but are bounded. So operator norm and trace can behave very differently. And these two quantities appear in the inequality. You see, below there is the sigma square, which is the lower bound, and above is the epsilon q, which is in the upper bound. Well, I denoted by epsilon q, not because it is always small, but because I want to look for cases in which it is small. Because I want that this inequality, the final inequality, gives me the information that the solution of the stochastic problem is close to the solution of the parabolic PD of the average. But you see, if we consider if the stochastic problem at the beginning is a first order hyperbolic, so to speak, it is conservative, the L2 norm is conserved, and therefore it's impossible that the solution of that conservative problem is close to the solution of a parabolic problem which decays. They could be close if they are observed in a certain sense, by a sort of modification, which is provided by this, by taking the scalar product with the test function. So both fields are observed by this test function, and under this smoothing of the test function, the solution of the non-dissipative problem can be closer to the solution of the dissipative one. This is a well-known principle in the theory of mixing also for deterministic problems. And so the constant here, theta 0 and phi, are not key. So all the question now is, can we find noises? Are there noises such that we have both the first and the second with small epsilon, large sigma? Sigma is the denominator, so large sigma, large trace of the covariance operator, small operator norm. Of course, yes, we can build operators that have large trace and small norm. Let us see concretely what we know about these operators. Here is the proof, but let me jump. The slides will be available, so you will see the proof if you like. I'm spending too much time on concepts, so let me miss the proof. The proof is not long. Let's go to good noise. Good noise. Repeat. Let's just repeat here that we need an upper bound and a lower bound, which imply this inequality. So epsilon must be small, sigma square must be large. And here is the example of Kreitner noise. Namely, Kreitner noise is a container with parameters. You can play on the parameters in many ways. I will show which parameters of the Kreitner noise produce the result I want. And so, for 1 minute talk, is not possible to read in detail this complicated spectral formula for the covariance of the Kreitner noise. Just notice that there is a scaling parameter. A scaling parameter, for instance, the theory Kolmogorov 41 corresponds to scaling parameter 4/3. Some people say 2/3, so there's a little debate between 2/3 and 4/3. If we take, and the scaling parameter can be positive or negative. So also the case when the scaling parameter is negative is very interesting, but it goes in the direction of space-time white noise. Space-time white noise. Or for instance, in 2D, already the so-called entropy measure in 2D is already with this parameter. No, precisely the parameter, if I'm not wrong, is 0 in the case of... Anyway, a positive parameter is a relatively smooth noise, even if it can be quite irregular. Negative parameter is very irregular noise. Here in this slide, I discuss only the case of positive parameter, but there are complementary results in the other case. And when the positive parameter, one can take here there is a cutoff in wave numbers, but one can take K1 infinite, the cutoff on K1. So forget about the cutoff on K1. The key point is that one should take a K0 large also. So if K0 is large, and the constant sigma square in front of the covariance is large, with a certain relation between the two, we have the properties above, which means K0 large means a noise at small scales. Small scale noise produces and high intensity sigma square, small scales with this link sigma written in the last line, we have the assumptions on that noise. And we have, for instance, a paper in which we have done this in bounded domain. Oh, maybe it's mentioned in another slide, but probably I should keep under control that my time is over in 20 minutes and not give all the details. We have, there are generalizations. maybe we can jump this. This is almost the same result. So forget about this slide. Bounded domains. So here is, I think this is very interesting to try to understand the effects of a boundary on this kind of problems. For many reasons, including the fact the noise which arises because of the presence of the boundary, but this is not the topic here. Here is, in a sense, the difficulties. This slide is about the difficulties of developing the same theory I showed in the previous slides, but in bounded domain. Why difficulties? Because for a viscous fluid, the fluid at the boundary is zero. Also, the covariance, if it is turbulent, and we describe with the covariance of a noise, this covariance must be zero at the boundary because of basic laws of mechanics. And so there is a degeneracy of the elliptic operator. The elliptic operator L, that was responsible of all the results, degenerates at the boundary. And this is a problem, in particular for the dissipation of heat, the passive scalar, because the dissipation of heat is due, in the case of bounded domain, is due to the fact that at the boundary I put heat, Dirichlet boundary conditions, so temperature equal to zero. This is a choice, but let's say, let's put this condition. And so the temperature, the heat is absorbed by the boundary, but at the same time, the turbulence that is responsible for this phenomenon of diffusion, of extra diffusion, the turbulence is zero at the boundary because the velocity field is zero. And so there is a little difficulty to cope with this, and one can introduce a parameter delta measuring the distance from the boundary of these effects, and at the end have quantitative informations quite good on the decay of the temperature, the true temperature profile of the stochastic case. The true temperature profile decays if certain conditions are satisfied. So we have a paper on this. I don't want to enter into the details of the condition, just to understand that some problem requires more care. For instance, this is a picture of the profile. This one is the profile without noise, and this one is the profile of the parabolic equation obtained by this procedure that I described above, which corresponds, at least qualitatively, it corresponds to the experiments. If we have a turbulence in a channel, the profile of temperature decay changes. Temperature decay or temperature maintained by an additional heat source. So if there is a heat source and a flow in a channel, the parabolic profile is for the temperature is what we observe in the laminar flow, and this fat and lower level profile is what we observe in the presence of turbulence. And so this theory explains, at least qualitatively, I didn't compare with experiments until now, at least. Open problems and difficult problems. Extremely difficult is to do a theory for vector fields. For me, I start to understand one phenomenon, which is not explained in this slide because I'm not still sure it's correct. In this slide is only mentioned this sentence from the book of, okay, so which equation we are talking about? So, sorry, M is a vector field, for instance, magnetic field, and this, there is maybe a small dissipativity and white noise, but as I strongly learned from Daryl, is absolutely important to put the noise both here and here. Or written with the Lie derivative. And so which is the problem? The first one, this one is very good. because is of a transport type in the sense like for scalars. It just produces a transport of the vector field. But the very critical one, of course, is this one. This one produces a stretching, elongation, maybe reduction, but statistically speaking, it's more important the elongation of the vector field, and so it goes in the opposite direction to what I showed before, because before I showed that the transport noise produces a sort of extra dissipation. Dissipation produces damping. This stretching produces the opposite effect. Understanding the balance between the two is extremely complicated. The dynamo effect, etc., is related to the link between the two. There is a sentence in this book, which claims that homogeneous, isotropic, mirror symmetric turbulence influences the decay rate of mean. There is this mean magnetic fields. The word mean, if it is taken strictly, in the sense that take the average magnetic field is such, it works. I can prove that it works. There is a decay of the average magnetic field. But if mean magnetic field is interpreted in something like in another sense, I don't know. So I don't know if this noise produces a dissipation or not in general. I think not, unless there are special conditions that between the noise and the magnetic field that could produce some form of dissipation. So, but this is the equation for the mean. By the way, the equation for the mean requires homogeneous mirror symmetric, but not isotropic. So under the assumption of homogeneous mirror symmetric noise, the equation for the mean is a parabolic equation which dissipates. But I cannot prove that the true random field is close to the average field in general. No, under any condition. I don't have essentially any condition, slightly general condition. There is obviously only one particular case that works when everything is two-dimensional. Two-dimensional is a fake problem when M is perpendicular to a plane where there is the fluid. The problem is two-dimensional, it works. So I'm investigating some other cases, but it's too early to give results. And instead of the linear passive, let's go to the non-linear. So the question is, what about this transport noise for Euler or Navier-Stokes equations? So here I wrote the two-dimensional case, because in the two-dimensional case, fortunately, there is only the transport part, if we want to add noise in the spirit of these theories. And so it moves to Ito plus this corrector, as many other speakers shown in their lectures for other versions of the equation. But at the end, of course, the versions could be very different between LU and SALT, etc. No, I'm not saying that everything is the same. I'm saying that the philosophy is that we move from Stratonic to Ito, getting an additional corrector. We cannot take expectation, so clearly we cannot take expectation, and but let's call oh, thank you, David. There was a comment. But let's call omega bar the solution of this equation. So omega bar, now there is a change of notation. Sorry for the possible misunderstanding. Omega bar is the solution of the deterministic equation with the increased elliptic operator, and is not, because of nonlinearity, is not the average of the random field. And, but now we ask if this omega bar, which is deterministic, is representative of omega, of the random field. So omega, is it closer to the solution of a deterministic problem? This would be called, in some literature, physical mostly, would be called eddy viscosity. Eddy viscosity. This operator L would be called eddy viscosity. Okay, it increases the viscosity of the turbulence. Turbulence produced by the noise at small scale, possibly at small scale, as we have seen from Krajner example. Small scale noise produces an eddy viscosity. If you open Wikipedia on the right page, you find exactly this sentence. I mean, so it's something that is recognized. The problem is whether we can prove this. And here there is not a question mark. We can prove this. We have in our papers, we have with Lucio Galeati and Junluo, we have this statement. The statement is made complicated by negative subgroup spaces, but nevertheless, we can prove that the solution of two-dimensional Euler equation and also Navier-Stokes. In the case of Navier-Stokes, we can drop the negative subgroup space. We can work in L2. But for Euler, we need the negative subgroup space in the philosophy of mixing proper and mixing results that are always in negative subgroup spaces. The solution of the stochastic problem is close to the solution of a deterministic with increased viscosity. And last 10 minutes, open problem. Okay, open in the sense there are contributions and something is still open. Where this model 2D, sorry, let me stress that this is still in 2D, to avoid this is in 2D, where this model with this Stochastic transport noise and maybe already some viscosity, where does it come from? So, of course, you are the group that developed the geometric approach with several justifications. There are also, using the geometric mechanics, justifications related to model reductions, so many. Here, I want to stress something which is very parallel, is more done a la Wonzakai. This is why I mentioned Wonzakai at the beginning. More a la Wonzakai instead by other arguments, an argument which seems to confirm that such equation erases as a scaling limit from an argument of small scale, large scale. In a sense, the noise replaces the small scales, which in the filtering, in many talks and papers that I have seen of your group, when you estimate or identify the covariance of the noise by means of the difference between cross-graining and the simulation. Essentially, this difference are the small scales, and so you use the small scale. So it's parallel to something that is done in the group that organized the workshop. So let me denote to understand the slides by U and omega, the large scales, velocity and vorticity, large scales. The U prime denotes this additional noise, which should be small scales. I advise with these two lines that I'm not solving. By this, I'm not solving the difficult question whether for applications it's more realistic to use energy preserving noise or Kelvin preserving or let's say entropy preserving in 2D, since we are in 2D, entropy preserving noise or something intermediate or another. I'm not solving that absolutely. I'm just saying that the following. I'm just saying the following. Consider this system. Consider this system. In this system, I decouple the vorticity omega in two parts, that one is understood like large and the other as small scales, but these are names because I just decouple the equation. This system is equivalent to Euler equation, is equivalent. If you sum the two equations, you get Euler equation. So this system is rigorously equivalent to Euler equation. So where it is that something is large and small scale. In the initial conditions, you put the initial condition for the two components to be the large and the small scales of the initial condition. And in the forcing term. So if we add the forcing terms, we decouple the forcing term between large and small. But one of the many open problems is for how long, for how much time the solution, the first component of this system is essentially large scales and the second component is essentially small scales. At time zero, it is by definition, but perhaps this is broken very fast and we don't have a result in this direction. What we have is the following. If we replace the second equation by this one, and for many reasons, including the difficulty to give an explanation, I just give the result without too many explanations. For instance, I could quote that if you see the works of Maida and co-workers on stochastic model reduction, this is very close. So it's very close to stochastic model reduction in the spirit of that community that was developed much earlier than us, 20 years earlier. If we do this, so if we replace the second equation by this one, we can prove that when the parameter epsilon goes to zero, the first equation, let me color in blue, the first equation converges to the model that we are talking about, the model with the Stratonovich transport noise. So it's a sort of Won-Zakai result, but in which the fields is not simply that white noise is mollified by mollifiers. It is a part of the Euler equation which converges to white noise. Omega prime, the omega prime here converges to white noise, due to the special scaling of this replacement of this. But I entitled open question these two slides because clearly there are many questions that raise and we don't have a precise answer. Let me converge to stop. The last topic, I will only mention something, would be regularization by noise, so well-posedness, but I will read more carefully your comment in 4 minutes. Sorry, otherwise I confuse myself with the regularization by noise. Regularization by noise is the question whether the noise produces additional well-posedness results with respect to those that are known from deterministic theories. There are positive results due to transport noise for passive scalars and for passive vector fields. So regularization by noise for passive objects is regularly powerful and well understood. We have the community developed something like 3-4 different techniques to regularize linear passive objects. Unfortunately, when we move from linear passive object to non-linear, that's more difficult. So if we take our Euler equation with transport noise, we are in trouble. Sorry, here there is a mistake of notation because this second U is a U prime, namely is the noise. Sorry. I denoted by U two things. So U prime is the noise, and the U is Biot-Savart of omega, of course. So this is the Euler equation written before with transport noise in 2 dimensions. Essentially, I don't have results of regularization by noise for this, except when we investigate very special vorticity fields which are given by point vortices. In this case, there is a result on no collision, which is new with respect to the deterministic theory. So it could be promising to understand the two-dimensional Euler equation and regularization. And the last comment in 1 minute, for the three-dimensional Navier-Stokes equation, unfortunately, I will come back to the questions in a second. Just complete in 1 minute my talk. For three-dimensional Navier-Stokes equation, it's a long story. I saw in the audience friends like Arnaud Debuche, César Besniak, and many people that shared 15 years of attempts to understand whether three-dimensional Navier-Stokes is regularized by additive noise, because this is the first attempt, additive noise. There is a chance that multiplicative noise transport type makes something good. Unfortunately, which is the problem? The difficult problem is that in the 3D case, we should add the noise in two places, in the transport, purely transport part, and in the stretching part. If we restrict to the purely transport part and make this honestly, namely projecting, which is very difficult. If we don't project, the equation has no meaning because it's an identity between some object which is projected and some other which is not. So there are no solutions. If we project the transport part, the equation is meaningful, well posed, and it is more well posed than the deterministic case. We have proved that there is a delay of the blow up due to this purely transport type. If we add the other term, the stretching term, the problem is open. So essentially, the 3D Navier-Stokes case remains open because we have used an artificial noise. Maybe in the future there will be progresses. It's very interesting to think to this equation like the large scales coupled to an equation for small scales like the one I wrote some slides before, in which the noise was additive. So an additive noise, but not an additive noise at large scale as we introduced for many years. An additive noise at small scales could be in some special scaling limit responsible for a transport noise, and maybe the transport noise is responsible for well-posedness. At the end of the story is the cascade of fluid and not abstract properties of functional analysis that would regularize. If this will be true, if it will not be true, I don't know. But so it's an attempt to use the true Navier-Stokes with the cascade instead of just abstract functional analysis in order to prove that 3D Navier-Stokes with the noise, with additive noise at small scales, could have a better property. Thank you very much. I think that I can jump these arguments about the 3D case and the literature, and I stop. Thank you very much.
Thank you, Franco, for this great talk. So I'm sure there is questions. So there is some questions in the chat. So Alex, can you read your question?
Yes. Noise by homogenizing in time. I understand. In the yes, in the philosophy of stochastic model reduction of the past, exactly is different. It's a little bit difficult to explain the difference. Let me try in one sentence. The stochastic model reduction tried, let's say, 10, 20 years ago was more objective, namely project the solution on large wave numbers and smaller, and apply a simplification of the small scales and take a limit. In this case, since it is a projection, it is large scale by definition, but the problem is that the final equations okay, they are good, but they are also more complicated than the LU and SALT and this equation that we are using today. They were more complicated with additive noise, as you say. This is about Beryl. Sorry, maybe I didn't answer any question. Let me read the which preservation is more realistic? No, it is one or the other. Could there be a transport model where both are, no, transport model with both conserved? I think not. I don't have a formal proof that there is no noise which conserve both, but all computation that we did for years, let's say, many people seems that there is not, unless maybe there is some example.
Constant coefficients.
Okay, thank you.
Yeah, I mean,
okay.
Other than that, I've tried. I also don't find anything.
Okay.
I can't find a condition.
Certainly, constant coefficients is okay. But in the chaotic, so to speak, chaotic noise, I don't think so. And which one is maybe indirectly, but with Daryl we discussed this topic several times, and I don't have enough. Certainly, Daryl has more explanations about which could be the correct one. I'm still trying to struggle. I think that in 2D, perhaps the vorticity is better, but because energy is transferred to large scales, so preserving energy in 2D, I don't know if it would be correct. Preserve the energy of large scales in 2D by a noise could be incorrect, but maybe there could be just a compensation to account for the injection of energy. So I don't know, maybe just a linear compensation could help to overcome the problems. So very difficult question for me. And if the vector fields in the noise are constant, sorry, thank you. Yeah. What you said, yes.
Yeah, go on, Chen.
I wanted to go back to the sort of deriving the equation and the partial results. I think this is very interesting. So if I understood you correctly, you separate scales initially, which is simply truth, but then you supplant the second equation with a noise equation. At that step, you're making an assumption, right? Simply separating, this is just the truth. But it's the point at which you say that the second equation can be, it has this form. That's an assumption. And that, of course, might not be true, that there is really a separation of scales of that form, right?
If I'm sufficiently fast. Here is the slide.
So,
yes.
The first is truth, like start from the decoupled system. If you sum them, you get Euler. As far as I see, there's no assumption there. It's the replacement of the second equation would be, this is your assumption. It's saying that there is it's sort of like saying there is a separation of scales, which might not be true.
Okay, let me explain what is assumption and what is not assumption. Putting this noise inside here as a forcing term is a question of modeling, so it's not an assumption. I could say that in my Euler equation there is an additive noise, and the additive noise affects only the small scales. So putting this noise is not an assumption. Putting this term is a question, namely, a lot of models in the literature about 2D Euler, etc., have a friction, because a friction in 2D is very natural. But this must be very strong friction, 1 over epsilon, very strong friction. So very strong friction is perhaps an assumption. There is a more difficult justification. I'm writing a book that maybe in a few months will appear. Another justification, noise appearing because of the emergence of vortices at the boundary. And when we do that kind of argument, we have to introduce an extra friction to compensate for the noise. We use noise to describe the vortices created at the boundary, but they introduce energy, because an additive noise introduces energy, and the vortices produced at the boundary, they do not introduce energy. They probably subtract energy because of the friction of the fluid with the boundary. And so we have to introduce a corrector which is more or less of the same size size, and so there could be justification for this term. There is another issue that the small scales are multiplied by two terms, and here I preserve only one term. I preserve only the action of the large scale on the small, namely the action in the sense of transport. The transport of the large scale on the small, I can preserve and prove the theorem. If I put also the self-transport of the small scale with the small scale, that is a bigger problem. That is related. Yeah.
I think maybe that's, perhaps I didn't phrase my question right. So the first system is the true Euler system.
Right.
And then if I'm understanding you correctly, you then start with, let's forget about that system. Let's consider a new system of the form with that. Then you do a homogenization result for that system.
Right.
But when I asked the question,
no,
because
what I want to say is the following, that these two terms you could put at the beginning. You could say at the beginning, I start from an Euler equation with an additive noise at small scale and a friction acting only at small scale that has a special origin, may be related to boundaries, and that. So they could be part of the equation at the beginning. But the fact that I neglect this term of self-interaction between the small scale velocity and the small scale vorticity, this is an assumption. This I'm not allowed to neglect that term, rigorously speaking. And so there is an assumption in neglecting that term.
But there's no hope, because on one hand you'd like to, I mean, sort of like the turbulence closure problem. You're saying let's consider this artificial world of a different fluid equation, and then let's prove a homogenization result for that. It's not saying like, let's take the real Euler system and let's show we can.
No, we are not yet in that position. In addition, let's say that this epsilon at the denominator here, of course, is a little bit forced into the equation. We wrote a justification, but in plain words, let's say, not. So I admit that this is still a very open problem. Much cleaner is the approach, also Daryl work decades ago, in which people projected the solution on but also in that case they had to make assumptions.
All they do is
I agree that there are always assumptions behind. At present, I don't think that anybody, in particular, sorry, I wanted to say something, but I forgot what I wanted to say. Namely, putting this epsilon at the denominator is like to assuming that there is a scale separation. And nobody can prove the existence of this scale separation. Thank you very much.
And from Daryl's approach, he has a paper on homogenization. And if you look at that and you try to figure out, well, what's the assumption? It's exactly, there is a scale separation.
Exactly. That is,
of course, there isn't, probably.
So, okay, yes. So perhaps the one assumption is that we neglect this self-quadratic term, and the other, maybe even stronger, is the scale separation. There are simulations in 2D in which it is relatively clear that large scales develop and small scale build a sort of noise which is quite separated. But when there is continuous reinjection of energy by small scales, this separation is broken because there is a continuous cascade. So all scales are activated. Okay, maybe.
Thank you.
I don't know. I'm not expert enough about that.
Thank you.
Maybe Daryl has a, okay, but perhaps.
Daryl, you have a question?
I just have a statement that this is a really interesting moment because as James Michael said, I assumed a scale separation, and it was a scale separation in time. Okay, so here Franco is assuming a scale separation in space. Now it's very interesting, I think, that to find out what is the equivalence of these two. Okay, is it actually possible, to get the same result by a scale separation in space or in time?
Very interesting question. Very interesting question. Yes.
Because Daryl does the homogenization just at the Lagrangian. There are some questions I have with that, but then he uses his geometric principle to close the equation to arrive at it. Whereas you're just starting directly at the Eulerian picture, doing a scale separation and going directly to essentially the same equation that he gets. So his sort of has scale separation followed by a closure model, effectively, which is, the geometric action principle picks off that, and somehow you end up at the same thing. It's a bit interesting. Yeah, it could be there is something.
I agree with Daryl that understanding the two scale separations, time and space, is very interesting. Very interesting.
Additional question?
Yeah, this has been a discussion in STUOD for a long time. Etienne derived his model thinking about a scale separation in space, and he interprets the problem in terms of small scales, large scales, and coarse scales and fine scales. That and generally the fine scales do go with the fast speeds, right? So the fine scales go with the high frequencies. And I just think that it's an interesting look to think in terms of the relationship between them, and and how you can. There's maybe some middle road where you make some assumption about how space and time scales are related, and then you can take this limit.
In this paper with Umberto Papalettera, we have a section precisely on the time, on rescaling, on time. We introduce 3 time scales, and we make some argument with the 3 time scales, but they are heuristic. I mean, it's just an attempt. So I'm not saying that we have understood completely the problem, but it's a very interesting question.
I don't see if there is anyone who wants to ask another question to Franco. Seems not. So thank you very much, Franco, for your great talk. It was really a pleasure to listen to it. So so we have 45 minutes for lunch, and then in 45 minutes we have the next talk. So thank you, everybody. So see you soon.
Hello, Etienne.
Hello. Daryl is not there. I guess he should arrive very soon, but okay.
Yes. We still have 3 minutes, something.
Yeah.
Daryl's here.
Oh, great.
Oh.
So I leave you the cheering.
Yeah.
Well, you can do it. Go ahead.
No, please. You will do it better than me.
Maybe we should wait 3 more minutes.
Yes,
We're
of
waiting.
course.
We're going to wait, of course.
Yeah.
We need to find out. Okay, so This is the afternoon session. And there's going to be, you've got 20-minute talks, and you should try to talk for 15 minutes and then leave a question behind so that people can, think in terms of using that time, but don't run over.
Yes,
okay,
exactly.
So there will be 3 talks at starting at 1 o'clock. There's Paul Platzert and Romeo Minsaw and Stuart Patching in that order. Is everyone here for this part of the session? So are you here, Romeo?
I see Romeo, yes, but...
Are you here, Stuart?
Yeah, I'm here, Robin.
Okay. So then when the question period changes, then stop sharing your screen and the next person start. And I'll just say who your name is, and then you can go, okay? So I guess why don't we give Paul an extra 25 seconds and let him start now. Go ahead, Paul.
Yes, sorry, now you can hear me, and I'm going to share my screen. And I suppose you can see the screen, you can see the mouse.
Yes, yes.
Yeah,
and,
all is well.
And it's moving. Okay, great. So as Daryl suggested, I'll try to be quick and not exceed 15 minutes so that we can have some time to talk afterwards. So the name of my talk is Intercomparison of Analog Stochastic Forecasts. And okay, if you're not aware what analogs are, here are a few examples. First on the this is a deterministic system, the Lorentz system. You may know it. And so this is a long trajectory inside this system. And if you look at one point towards the end of the trajectory and you go back in time, you can actually find that the system went close to this target state also in the past. So analogs are states that are close in physical space or representation space, but far away in time. And if you look at the real data, here's an example with wind, surface wind. You have similar types of recurrences, especially for atmospheric data. So here, for instance, this date in 2017 is quite a good analog of this date in 2019 in terms of surface wind across the coast of Brittany. And here's another example where the variable is not wind, but it's sea level pressure. And again, these dates are far away in time, but the states are similar. Okay, so these are what analogs are. Now, there are many things that you can do with analogs, but I will talk only about stochastic forecasting for applications for the atmosphere and the ocean. And I'll talk about 4 different methods. So I hope this will give you an idea of all the possible ways that you can use analogs to make a stochastic forecast. So not deterministic, but stochastic forecast. And for the other uses of analogs, there are many. And if you're interested in, I encourage you to go and look at the bibliography at the end of the talk. So these 4 methods that I'll be talking about, they all belong to the field of analog forecasting, but they also belong to other fields, numerical weather prediction, stochastic weather generators. The analog data assimilation is, of course, related to data assimilation, also to machine learning. And this method, kernel analog forecasting, takes ideas from time series forecasting, from machine learning also, and has a real good description in terms of dynamical systems. Okay. And if you go out of the atmospheric science or ocean science community, you might hear other names that also talk about the kind of methods that I'm going to introduce. So in machine learning and time series forecasting, people talk about lazy learning. So why lazy? Because in these kind of methods, you don't compute anything until a query is given. So you're not going to fit a big complicated model with lots of parameters and then store those parameters and apply this model on any new query. No, what you do instead is you keep all the data, and then once a query is given, you fit a model to the data, but depending on the query. So that's also the reason why it's called. So it's lazy because you wait until the last point until you get a query to compute parameters to fit a model, and it's also memory based because what you store is actually the whole data that you have. And once you get a query, actually the query, the way I called it in the beginning was a target. Once you get a query, this is the way that you're going to fit a model to your data is that you'll fit a model to the closest elements in your data to the query. So you're going to fit a model in a neighborhood of your query. And so that's why it's called k-nearest neighbors, local learning, local method, local model, etc. And in the statistics community, you would hear people talk about non-parametric methods. So for the same reason, it's because you store data, not parameters. Or you could also hear kernel regression or kernel method. And this is because once you have your neighbors, you're not going to give equal weights to all the neighbors. You're going to give more weights to the neighbors that are close to your data. And this is usually done using what is called a kernel function. Okay. Now, throughout this talk, and when I'll talk about the 4 different methods, I will assume that behind there's a dynamical system, which is unknown, which involves the states and time, and that I have 2 types of variables, the covariate and the response variable. And so the task of making a stochastic forecast from analogs is usually if you have a given response variable y, so this is the variable that you want to forecast. So this is fixed. Let's say someone asks you to make a forecast about temperature. And so y is fixed. And so once y is fixed, the first thing you have to do is to choose appropriately the variable that's going to explain the explanatory variable. So you have to choose appropriately x, and then you have to estimate this kind of probability, so probability of y at a later time t plus tau, given the observation x at time t. And you do that using what is called a catalog of time ordered realization. So it's your database of realization of this process. Okay. First method, the analog ensemble. Here, the idea is that if tau, the time at which you want to make a forecast, is 42 hours. So here you're going to start with the 42-hour numerical weather prediction, the deterministic one. So this is something that is always computed by numerical weather forecasters. So it's always available. You can always start from this prediction. You don't have to compute it again. And then you go back in time and you go into your catalog and you look for past 42-hour numerical weather predictions, deterministic. So what was the prediction in the past, the 42-hour numerical weather prediction? And you take the similar ones, you take the analogs, and since it's in the past, you also have the observations corresponding at that same time. So you can use that, you can use these observations corresponding to these analog forecasts, analog deterministic forecast, to make an ensemble for any variable that you have. So in our notations, the covariate is the numerical weather prediction at time t plus tau. So in the paper, they actually use a kind of time embedded version of this. And the response is any available observed variable. So this has many advantages. It's fast, it's simple, it's tailored to real atmospheric data. what is nice is that the baseline is something which is already operational and very informative. That is the deterministic numerical weather prediction forecast. And you know, I can show you some figures, but you know, in their study, they say that this can outperform some state of the science numerical weather prediction ensemble. So if you don't know how these are generated, usually if you want to have an ensemble of possible future observations, what you can do is you can rerun numerical weather prediction, so simulations based on a physical model, and just change slightly the parameters and the initial condition. This will give you an ensemble, but this has a very high cost. And on the other hand, this method is very simple and very low cost. There are many open questions still. There's a lot of hand tuning in this method, so maybe that could be optimized. To my point of view, there's a lack of dynamical systems formulation. It would be nice to really understand what this method is doing and to test it on idealized systems. And there is a potential risk near a bifurcation point, and we can see that later if we have time, but I don't have the time to explain you exactly what I mean here. Okay, second method, the analog weather generator. So here again, it corresponds to a particular choice of the covariate space. Here, the covariate for this method, it has to be a pressure field. So it can be sea level pressure or geopotential height, which is more or less pressure as well. And the idea is that you're going to generate trajectories of X, and then from these trajectories, you're going to extract observations Y. So how do you generate the trajectories X? Here is an example. This is one trajectory, one possible trajectory, and I'll lead you through the steps of how this is generated. So you start from an initial condition, okay? And then you select analogs of this initial condition. So these lines, think of it as the Lorentz model that I showed in the beginning. They're actually from the catalog from times in the past, but they're just close in space, in X space. Okay, so these are analogs. I assume that we take just two because it's easier to show. So the first thing that you can do is you can go to one of the analogs of the initial condition, and then you go forward in time. And then at each time step, so you go just a small time step ahead. And at each time step, you have two choices. Either you go to an analog, and then you go forward, or you can stay on the same trajectory and then go forward. And the probability that you stay on the same trajectory at each time, it's something that is fixed. It's a hyperparameter of the model. So this is, so you see here, you take one of the analogs and then you go forward in time. Here in this example, you stay here and then you go forward in time, etc. And then you arrive there at time t plus tau. And just to give you another example of another realization of the exact same process, it could be this one. Starting from the same initial condition, you could actually go to this analog and then go forward in time, and then stay here and then go forward in time, etc. Okay, so I hope that you get it. Here there's a one more hypothesis, is that this choice of X gives that X is close to a stationary Markov chain, and then with that you can generate any kind of observation. So again, this method is fast, simple, it's tailored to real atmospheric data, and also we can talk more about it, but it's also able to simulate extreme events, because this method can be coupled with something known as importance sampling. So it's a very interesting weather generator. There's a lot of open questions. Why doing iterated analog forecast rather than direct analog forecast? What do I mean by that is, if I go back here, rather than going through the steps of searching for analogs at each time step, you could say, okay, I just start there. I look for not just 2, but maybe 20 analogs. And then I go directly from time t to time t plus tau. And that would give me an ensemble. And that might be much cheaper than looking for analogs at each time step. So it's a real hard question to know what's the advantage of splitting the forecast into these time steps. And there's a lot of answers to these questions from the time series forecasting literature, and the connections have not been made yet. So I think it should be made. Also, again, there's a lot of hand tuning. And again, I think it lacks some dynamical systems formulation and tests on idealized systems. I think I should go a bit faster now. So the analog data assimilation, basically, let's say it's similar to the analog weather generator, but it's not. It does not correspond to a special choice of x. X doesn't have to be sea level pressure or geopotential height. But as I said before, it doesn't split the forecast. It goes directly from time t to time t plus tau, and if there are 3 different versions of the forecast part of this method, depending on the choice of S, the matrix S here. And if S is 0, this is exactly as the analog weather generator. So you just go from one analog to its successor, and that gives you that kind of ensemble. This method adds S equal identity matrix. So it just gives an increment added to the successor, and this can be advantageous for small time steps, but that's all. For large time steps, it's not really useful. And another way is to make a local regression between analogs and successor, and to use this regression for the matrix S in this formula. And in this case, it can be much more precise, but it's a higher computational cost. What are the advantages is that these methods have been combined successfully with data assimilation. It's fast and simple, and it has been tested on many different systems, and it's working quite well. Okay, I should be even faster. Okay, there may be some problems, especially in the forecast error estimation. We can talk about it later, but again, I think using methods from time series forecasting would help to improve. And now I'll be very quick because I'm over already. So this last method, basically, so there's a lot of math here, but we don't have to go through it. What's important is that it's kind of, it's like the linear regression here, but there's a kernel reproducing Hilbert space trick, let's say, and what happens is that you're going to project your data on a suitable base of eigenvectors of a kernel matrix. You have to choose a proper kernel to do that. And what is really interesting with this method is that you can you really have some proofs that in the limit of large data, what you're going to compute is going to be a good estimation of the mean of y at time t plus tau given x at time t. And also, you can also compute not just the mean, but any other moment or statistically relevant quantity using this method. So it's a kind of analog forecast, but you're computing not ensembles, but moments. And what is nice is that you have guarantees that it's working if you have a lot of data. And it's not limited to particular choices of X and Y, but still, you know, okay, there are some questions, but I think I should stop now because I want you to ask me questions, and I'll just stop now and ask me any question like.
Right. So thank you, Paul.
Thank
so
you.
Actually, go back to your open problems. The one more back. Not
okay.
One more. I'll open questions. Yeah.
This one?
No. At the very end. At the very end, you had some open.
At the very end. Okay. Like the future research directions.
Yeah, future research directions. So are there questions? Let's see. I don't see any questions for Paul. Does anybody want to raise their hand? Okay. So Paul, I wonder what happens sometimes if some of these methods actually is it appropriate for time series? Okay,
Yes.
just to apply the methods for time series. And
yes, it's been applied a lot to times. Yeah, sorry.
Yeah. So, all right. So if you have comparing all different approaches in the unifying framework, what'll be the unifying framework?
Yeah. So I think that that would be the unifying framework, and so this framework was actually the one that is used by the people who use this method, because it allows them to prove that that they're really estimating correctly the moments of the distribution in the limit of large data. But I think that would be nice to compare in experiments what happens, because it's not clear how fast is that convergence. It's not clear at all. So that would be interesting, because they have to use actually a lot of eigenfunctions and sometimes a lot of analogs for it to work. And this method is a kind of more involved version of the previous method, and it would be nice to see what's the real gain compared to the previous method, which can be seen as kind of weighted averages, or just weighted statistics. And also there are some questions regarding the applicability to high dimensional space of this method, and maybe that
I have, thank you very much. This talk raises a lot of questions. Okay, but time is up for the question period. So let me just call now on Romeo to start his talk, and could you stop sharing?
Oh, I had another quick question, actually, if possible.
We don't have time.
Okay, then.
You have to talk to Paul offline.
Okay, fine.
Okay, we can do that, Louis. Okay, I will stop sharing now.
Okay.
Can you see my screen?
Is it where Romeo is sharing? Okay.
Yes, I see your screen.
All right, great.
Okay.
So this is part of the central theme, and is this TQG. So I'm looking forward to hearing what you have to say, Romeo.
All right, thank you. So today I'm going to discuss the main subject of my my work for the past year, and it's almost entirely on the thermal quadratic equations. Oops. Right. So yeah, we've already seen the thermal quadratic equation in a few talks already. But just to recap, it's just a model for fluid dynamics that generalizes the classical TQG, or generalizes the classical quadratic equation by incorporating thermal effects which are known to affect the buoyancy in a fluid. So here, given a set of data sets which includes the initial potential vorticity, the initial buoyancy, the correlates parameter that give information on rotations in the fluid, and the bathymetric gradients that describes the topography of the ocean.
Well, yeah, I mean, we're still looking at your first slide. Have you?
Can you see the equation for the TQG?
Yeah, I think you should be on the next slide.
Yeah, I'm on the slide 2.
No, it's not showing that way. So okay. You need to scroll down or something. See, can you make it scroll?
Oops. Sorry. Can you see now?
Yes, that's it.
And is it moving?
Now it's working.
All right, great. So as I was saying, given this 4 set of data, that's the initial PV and buoyancy, the correlates parameter and the bathymetry. What we are interested in is to construct a buoyancy PV pair that solves this coupled system of equations. So in a recent work with Dan Chris and Darrell Holmes, Eric Lusick and Wei Pan, we are able to show that the Tqg equation is locally well posed in the sense of Hardeman, right? So in particular, we are able to find a time t for which we can find a buoyancy potential vorticity pair that solves our equation pointwise almost everywhere in space-time. And this pair has this regularity. So the buoyancy is continuous on the time interval with values in the subatomic space W32. The potential velocity is also continuous on the same time interval with one less regularity. We can show that this solution is unique. So one can trace back trajectories of solutions. And finally, we can show that the solution is also continuously sensitive to perturbation in its initial state. So this is important for numerical analysis because it says that if initially we have 2 solutions of the Tqg that are close to each other, then as time evolves, they should remain close to each other. Now, there is nothing deep about the construction. It's just the usual energy method. Where if you want to construct a buoyancy with certain regularity, you take the equation for the buoyancy, you differentiate a certain number of times, test with the appropriate differential of the solution, do integration by parts. Right. So now the story goes that when the Tqg was introduced in the framework of STUOD, the idea was to perform some numerical studies of the Tqg. But there were some numerical challenges, which I don't go into because I don't have a full appreciation of it. So due to these numerical challenges, a regularized version of the Tqg was introduced, which you call the alpha Tqg. So this solves the numerical challenges. And the only difference between the alpha Tqg and the Tqg is that the way the potential vorticity is derived from the stream functions is as a function of a 4-order differential operator. So you have this 4-order differential operator here. And beside this extra operator, everything else remains the same. So this regularizes the system in a way. And one can easily observe that if formally you set alpha to be 0, then you obtain the original Tqg. Right. Now, as one would guess, if you have a system, you consider a regularized version of it. If the original system is well posed, then of course the regularized version will also be well posed, and you're able to show that in our paper also. So for any fixed alpha, we can show that the alpha Tqg is also well posed. Now, not only are we able to show that the alpha Tqg is well posed, but we're also able to show that the alpha Tqg serves as a nice approximation of the Tqg, in the sense that if you take any family of solution to the alpha Tqg parameterized by this alpha in the differential operator, the extra differential operator, one is able to show that this family of solution will converge in norm to the solution of the Tqg, provided that they share the same data. Why? I mean, this is to be expected. If you want 2 solutions to coincide, they need to coincide initially. So you expect the initial potential vortices to be the same. The topography of the ocean under consideration should be the same. The information on rotations in the fluid should be the same, right? So once these things are satisfied, you're able to show that the alpha approximates the Tqg in a way. Yeah, for mathematical reasons, this analysis work on a slightly bigger space than the space of existence. So you have a lower norm described on an extended space, and it's on this extended space that we're able to show this convergence result. And again, here, the tool for showing this convergence is the relative energy method, where instead of taking norms of the solution, because you are comparing two solutions, you take the norm or the difference of the two solutions for the two systems, and you show that the difference in this norm converges to zero as alpha goes to zero. Right. Now, at this point, what we've seen, to recap, we've introduced the Tqg. We've seen that it's locally well posed, but due to certain numerical challenges, its regularized system was introduced. That is also well posed, and beyond that, it nicely approximates the solutions of the Tqg. Now, what we see is that this result is just a local result. So as is usually the case in fluid dynamics, you want to see what happens beyond the existence of the known existence of a solution. And in certain cases, it is known that solution blow up. So in the next part of our research, what we wanted to explore is this blow up criteria. So in other words, to ensure that the solutions behave nicely, what are the quantities you need to control, or what affects the lifespan of the solution of the Tqg. Here we take the solutions of the alpha Tqg because it's the more regular of the two systems. So if something messy happens to it, one will naturally expect the same thing to happen to the Tqg, but not vice versa, right? So it takes the alpha Tqg, and then we're able to show that to ensure that the solution of the Tqg is well behaved. There's no blow up in the solution of the alpha Tqg. It turns out that you need to consider a certain Buckner space, L1 in time, L infinity in space. And in this Buckner space, the theory says that if you can show that the buoyancy gradients, so the changes in the buoyancy, is controlled for all time, then you're able to analytically show that this will ensure that the solutions of the alpha Tqg is also controlled for all time. Now, alternatively, it turns out that this buoyancy gradient do not have like a monopoly on the behavior of the solution of the alpha Tqg. So rather than taking or controlling the buoyancy gradient, in the same Buckner space, one can instead control the changes in the velocity. So control the changes in the velocity will also lead to control of the solution of the alpha Tqg. And this is an inclusive OR statement. So if for some reason you have a lot of time on your hands, you can also control both of them simultaneously to get control on the solution of the alpha Tqg. So to see why these two quantities sort of have the control of the solutions in their hands, it turns out that analytically, and this is just an analytical statement, I don't know if it translates physically, but analytically, it turns out that these two quantities are equivalent in a way. So we're able to find, this means that we're able to find two constants. That only depends on the data. Mind you, the data are time-independent data. So we have the initial buoyancy, initial PV, the Coriolis parameter, which is also time-independent, and the bathymetric gradient, which is also time-independent. So for such constants, we're able to show that if one of the quantities is control, then automatically it leads to control on the other, and vice versa. So to see why this is the case, you just have to take a look at the a priori estimate, right? So yeah, you take the equations, you differentiate appropriately. And what you're able to show is that the time derivative, the changes in time on the solution in the space of existence. So this is the norm prescribed on the space of existence. Satisfy such a bound, this. Now, because we are considering the alpha TQG, and this perhaps the main point, its regularization effect means that we are able to control the velocity gradient in the Buckner space under consideration with the entropy in the system. So this property does not hold for the original TQG, it just holds for the alpha regularized version. So you're able to gain this control with some constant that depends on alpha, which of course is also time independent parameter. Now, on the other hand, if you take the equation for the potential vorticity and it tests with itself, it also gets such an exponential bound for the entropy, right? So having these two inequalities, one observed that if the buoyancy gradients are controlled in the Buckner space I mentioned, then that will lead to control in the entropy. And then the entropy in turn will lead to control on the velocity gradients. So having control on this leads to control on that. And then because this guy is the same as this guy, we're able to apply Grunwald's type arguments to get control on the solution. Now, alternatively, to see how the velocity gradients control the solution, we take the equation for the buoyancy, we test with the Laplacian of the buoyancy, we do integration by parts, and then we obtain such an exponential bound for the buoyancy gradient. Now, on the other hand, we also have this entropy bound from the previous slide. So having these two inequalities, we observe that control on this guy is to control on that guy, which in turn leads to control on the entropy. So again, we obtain control on this, and by Grunwald lemma, we obtain control on the solution. All right. So to recap, we've shown that the TQG is locally well posed. It has a regularized version, alpha TQG. It's also locally well posed. It approximates the TQG in the sense of convergency norm. And moreover, these two quantities, the velocity and buoyancy gradients, control the behaviors of the solution. So, I mean, my time is almost out, but as a teaser, one would expect that the next natural step is to introduce noise into our system, because in the framework of STUOD, the goal is to model uncertainties in fluid by the introduction of noise. So yeah, we introduce as a source noise, where stochasticity is incorporated into the system by way of some one-dimensional Brownian motions. And then we have this observational data psi i's, which in a way kind of like mimic the behavior of the velocity field. So these psi i's are just some time-independent vector fields that are also divergence-free. And then our goal is to construct an equivalent notion of a solution for this stochastic system. So we want to construct a solution that is strong in the sense of PDE and strong in the sense of probability. So the solution should be satisfied pointwise almost everywhere in space-time. And rather than it being a material solution, we expect it to be a pathwise solution. So I'll end it here. Thank you very much.
Yeah, thank you. Thank you. Very clear talk, Romeo.
Thank you.
So we have 4.5 minutes for some questions. Let me, are there any questions on the chat?
No, not for me.
Okay, so let me see if I understand something here. So if you take alpha to 0, and for every subsequence going to 0, if you haven't blown up, then no, actually, here you have full control, right, for the thermal for TQG. For every subsequence going to 0 of alpha going to 0, these results remain, right?
You're talking about this, right?
Yes, right.
Yeah, so here what you're able to show is that any family of solution, I mean, I'm talking about subsequence. I mean, just take any family of Tqg. So take the system parameterized by some alpha, and then we're able to show that if you just take the solution of this, the difference of the solution of that, B alpha, omega alpha, and that of the Tqg, then in some norm, we can get some exponential bar that depend linearly on alpha. So because of that dependence, it just means that as alpha goes to 0, the norm of the difference will also go to 0.
And you also have uniqueness of Tqg to start from, right?
Yep.
So each sequence, if you take a different subsequence, then they will all converge to the same solution of Tqg.
Yes.
Right.
Yes.
Yeah. So this is a big accomplishment. Does anybody else have any other comments? I have another one to ask. The other question I have is, what if you, is I don't see any condition on the gradient of the bathymetry here. Is there a condition on the gradient of the bathymetry?
The only condition we have is that it should mimic the regularity of the anticipated solution for the buoyancy. For the analysis to work, it somehow needs to, I don't know what that means physically, but you need to mimic the regularity of the anticipated buoyancy. Whereas there seems to be like this one-on-one thing. So this one, the correlates parameter mimics this behavior, the bathymetric gradient mimics the buoyancy. Maybe there can be some physical interpretation for it, but mathematically, that's all we need. That's the only condition we need to impose on it.
I'm really impressed by that because grad H is controlling the solution, for the transfer, between vorticity and between circulation. Well, it produces circulation whenever grad B is not aligned with grad H, and so you have you could have a very large multiplier of grad B there if grad H was large. But you're telling me that as long as grad B stays in W32, then all this still holds regardless of what grad H is doing.
No, grad H should be in W32.
Okay.
Yeah.
But that's still very impressive. Okay, so yeah. Is there any other comments? Okay. Thank you very much, Romeo. This is a really nice talk.
Yeah, thanks.
And your time, right on time. Okay. So Stuart, are you ready?
Yeah, I think so. Can you hear me okay?
Yes.
Okay. Can you see my screen?
Yes.
Okay, shall I begin then?
Yes.
Okay, so I'm going to talk today about stochastic advection by Lie transport, which is a method for adding stochasticity, which I think many of you are already familiar with. And I'm also going to talk about a new method called stochastic forcing by Lie transport, or SFLEET, we call it. And I'm going to talk about how these two methods can be implemented into the primitive equations. So just to, okay, why is it not changing slide? Okay, so just to outline my talk. So I'll first of all talk about the primitive equations. So the primitive equations are important because these are probably the most commonly used set of equations in practical ocean modeling, used in MIT GCM, ICON, Phazon, many models. And so it's important if we're developing these stochastic parameterization techniques that we can implement them into practical ocean models. So I'll talk about how you can derive primitive equations from a variational principle, and therefore how you can include salt and SFLEET into the primitive equations. And then I'll just go through some of the properties of these equations, such as the Kelvin circulation theorem and energy conservation. And then I'll go over some details on how we go about implementing this in a practical model. In particular, one of the big challenges is how we configure the noise. So for SALT, because it's a method where we put the noise in the transport velocity, we configure the noise by looking at Lagrangian paths. And for SFLEET, it's well, I'll explain that we modify the momentum, and therefore you look at the Eulerian differences is what you're modeling. So this affects also how you configure the noise. And then, yeah, there's just some technical details about how you do the coarse graining. So in an ideal setup, we use a fine grid and perform a coarse graining on that grid to get a representation of the large scale solution. But how you actually do this coarse graining is not so straightforward. And then I'll present some preliminary results, but this is very recent work, so there's not too much detail in the results so far. So just an overview of the primitive equations. The key point about the primitive equations is that there's a big distinction between the horizontal and vertical velocities, because on oceanic scales, the horizontal scale is much larger than the vertical scale. And so we can approximate the vertical velocity as being much smaller than the horizontal. And therefore, we only have a prognostic equation for the horizontal velocity, while the vertical velocity we determine directly from the incompressibility condition. We also have the pressure given by the hydrostatic balance condition, which replaces the vertical velocity equation. And this gives the vertical derivative of the pressure, which depends on the buoyancy B, which is given by the equation of state, which can depend on the temperature, salinity, and other variables, and also on the vertical height. We also have the inclusion of tracers, such as temperature and salinity, and these obey an advection equation. There's also, you can take into account the free surface as well. So we want to include all these factors in a variational principle. And to do that, we need a Lagrangian. So it turns out that the correct Lagrangian to get the primitive equations is this. So take the kinetic energy. So this is the kinetic energy only with respect to the horizontal velocity. So I'll use U to denote the horizontal velocity and V to denote the three-dimensional velocity. So we take the two-dimensional kinetic energy, this term, which gives us the Coriolis force, and then subtract the potential energy. And then you integrate with respect to this density D, which is defined in terms of the diffeomorphism G, which maps each particle from its initial position to its position at time t. So the Jacobian of that map gives you this density, and that plays an important role as an advected quantity. So yeah, as I said, R gives you the Coriolis force, and V is the potential energy, which for primitive equations needs to take this form. So the vertical derivative of V holding T constant is given by G times 1 plus the buoyancy. And here I've just assumed that salinity is constant. So I'll only talk about one advected tracer, which will be temperature. So this is the Lagrangian description. If we want to move to the Hamiltonian form, which will be useful when we're talking about energy conservation, we need to do the Legendre transformation in terms of this momentum M, which is given by the variational derivative of the Lagrangian with respect to U. And so we can write that down. And so this consists of two terms, the first one being the kinetic energy and the second one being the potential energy. So not too unexpected. So then we can use this to do the variational principle. And if we do it in terms of the Hamiltonian, then it works out quite nicely, because we can see how to include SALT and SFLEET at the same time. So for the deterministic case, the variational, or the action looks like this. So we have the action principle is 0 is delta S, and S is this thing inside the integral. So these first two terms are basically the Lagrangian or the Legendre transform of the Hamiltonian. This third term is unique to the primitive equations because in this case, the W, which will turn out to be the vertical velocity, or the vertical transport velocity, I should say, acts as a Lagrange multiplier, enforcing that the third component of the momentum is 0. So this M on its own is the horizontal momentum, and M3 will be the M3 in bold will be the 3-dimensional momentum. And then M3 in not bold will be the third component of that. So we have this term enforcing that to be 0, which gives us primitive equations in the form we want. Then we have the incompressibility condition forced by this, or enforced by this pressure, which is a Lagrange multiplier. But here it's stochastic because we're dealing with stochastic quantities. So the Lagrange multiplier has to be a semi-martingale in order to enforce D equals 1. And then these terms are, these alphas are Lagrange multipliers that enforce that the advected quantities, which I've here just denoted Q, but that will include D and T, that these are advected. So then so far this is the deterministic variational principle. If we want to make it stochastic, then we have two choices, either SALT, which are these terms in blue, so we can add on a series of stochastic Hamiltonians, or SFLEET, which uses the Lagrange-D'Alembert principle. And so what we do is we add on a term that is delta dx. So there's no action. So in general, F can be anything you want. So there's not in general an action that will give rise to this variation. So with the Lagrange-D'Alembert principle, you need to put this in sort of by hand. But then F can be theoretically anything. And we'll see in a bit what we need to choose that to be. So yeah, just to clarify the notation, got M3 and then QI are just shorthand for these advected quantities. So we can crank the handle of the variational principle to get our equations of motion, which will give us so that the transport velocity dx is given by this term. This drift term is the deterministic transport velocity that you get normally, and then if we're using SALT, we get these additional stochastic terms, which we usually denote by Xi. So Xi I is equal to dhi by dm, and then this term will just be v, the 3-dimensional velocity. So SFLEET in red adds this extra forcing term to the definition of the momentum. So here we see the difference between SALT and SFLEET. In SALT, we're modifying the transport velocity, whereas in SFLEET, we're modifying the momentum. And yeah, so the first two parts are just the diamond terms, which are defined like this. And then the remaining equations are this will give you the continuity equation, which will in the end be the incompressibility condition, the tracer advection, and then the advection of these two terms, which will give rise to the momentum equation. And then we have this condition D equals 1, which combined with this gives the incompressibility. And then this is, as we said before, the third component of the momentum is 0. So we have a horizontal momentum. So we can combine these to get the equations of motion. So if we take the time derivative plus Lie derivative of this M3, we get the momentum equation. So we see that in SALT, the only difference is that our dx has this blue term in it, and otherwise the equation is the same. And with SFLEET, you just take away, you shift the definition of momentum. And in both cases, you get the transport velocity being divergence free. So what does this mean in terms of conservation properties? So salt conserves the Kelvin circulation theorem, but the loop around which you integrate is advected stochastically, whereas Fleet has a deterministically advected loop, but it's the momentum that changes. So we can combine these together. So salt, you see no blue terms in here. That's because the only effect of salt is to change what this definition of C of T is. And we see that the circulation is generated by buoyancy gradients being not flat. But then Fleet gives this shift in the momentum. So this will give, if you define the circulation in terms of the original momentum, then you'll get some additional forcing on the circulation, unless you choose F to be this very restricted case where it's a gradient, and then obviously the integral will be 0. So that's the circulation and how it relates to salt and Fleet. Another property we might like to consider is energy conservation. So to do that, we need to write our equations of motion in terms of a Lie-Poisson operator. And so we do that on the next slide. So we see that here, we've just written the evolution of M, D, and T in terms of this operator acting on the variational derivatives of this stochastic Hamiltonian. So we can see, first of all, with salt, because the Hamiltonian is now stochastic, this causes problems with the conservation of energy, because if we want H to be conserved, then when we take the time derivative of H, we'll get on the right-hand side these extra stochastic terms because of HI. So energy won't be conserved for salt. But for Fleet, we see there's 2 extra terms. So we have this dF up here on the right-hand side, which could potentially cause a violation of energy conservation. And then this term in here, which is not too much of a problem. But it turns out that if we choose F to obey this particular time evolution, where the time derivative plus the Lie derivative is given by a total Lie derivative, then we can just absorb this dF under here into this Lie-Poisson operator in terms of this new variable d phi, and then this operator will be anti-symmetric and will therefore conserve energy. But it does mean we have to choose F to be this very specific form, and then we'll expand d phi for Fleet in terms of these xi's. So overall, salt conserves the circulation theorem, and Fleet conserves energy. So just to compare the resulting equations of motion, in salt you have this modified transport velocity, and this gives rise to these blue terms on the right-hand side of the momentum equation. So you have this curl of U cross psi plus a Coriolis term plus a shift in the pressure. And you also have an extra advection term in the tracer equation, and the condition that the psi must be divergenceless. And then we get from the hydrostatic balance condition this extra stochastic pressure term, which is given by this equation. And then Fleet in the equations of motion is very similar, but you'll notice that the curl term is curl of psi cross V instead of curl U cross psi. And there's no Coriolis term, because this term that you add is effectively a Coriolis term, because F cross V is the normal Coriolis force, and so you're effectively modifying that by this curl term. And the tracer is advected deterministically. So interestingly, if you compare the Craig-Leibovich equations, which were developed as a parameterization of the interaction between surface waves and the flow in terms of this Stokes drift, we can see that if we compare with the salt equation, the terms that you get are exactly the same as what we see in salt. You have this Coriolis force acting on the Stokes drift, as we have the Coriolis force acting on psi. You have a shift in the pressure by U dot US in Craig-Leibovich and U dot psi in salt, and then you get US cross curl U, where we have psi I cross curl U up here. So interestingly, salt is a stochastic analog of Craig-Leibovich. How am I doing for time? Okay, so I'll go quickly through the rest. So to do the numerical implementation, we use Euler-Mariana, the simplest method. So to do that, we have to convert to Ito form. And this is fairly straightforward for salt because the right-hand side of the momentum equation in these stochastic terms only depends on U. So we just get this some operator squared acting on U. So we can just run this operator twice to get that term. And similarly for Sleet, it's a bit more complicated because you have du depending on V in the stochastic terms. So as a simplifying assumption, we take that psi is only horizontal and independent of Z, which may be a bit of a restriction, but it simplifies quite a lot. So you just have this one stochastic term to worry about, depending on U, plus the Ito correction. And yeah, a large consideration is how you calculate C's. So in SALT, we calculate C's by integrating Lagrangian trajectories. So you take a fine grid solution and integrate a Lagrangian trajectory. You take a coarse-grained version of that solution and get another Lagrangian trajectory and look at the differences. And then you take the empirical orthogonal functions of those differences to get your X's, and use the Lagrangian trajectories because in SALT you're parameterizing the uncertainty in the transport velocity. Whereas in Sleet, it's a bit more straightforward because you're looking at Eulerian differences. So it makes sense to take as your X's the Eulerian difference between velocities. So you don't need to worry about integrating up the Lagrangian trajectories. But there is a bit of subtlety here because we would like F to be the sort of correction to the momentum, but we need it to be in this particular form in terms of the Lie derivative of phi. But yeah, and then it's not easy to relate phi, like given F, to calculate phi. So what we do as a kind of hand wavy resolution is just to use psi's as d phi. And then, yeah, just to give an example, the way we do the coarse graining to get the, because we take the difference between the fine grid solution and a coarse grained version of that. If you use different filters to do that coarse graining, you can get quite wildly different results. So using a Gaussian spectral filter gives a very kind of smooth and strong EOF. Whereas if you do like a top hat filter where you just average over points in a local box in physical space, then you pick up a lot of small grid scale features. And so it seems like an important consideration how this coarse graining is done. You can also compare the spectrum of the EOF, so the eigenvalues, and see how many you need to get a certain amount of variance. So you see that with the Gaussian filter, you get a lot more variance with fewer EOFs. So just to show some preliminary results, I used sort of square idealized domain with wind-driven flow, 16th degree for the fine grid and 4th degree for the coarse grid. And so far I've just done I've done some initial basic runs with only 8 EOFs, which may be too few. And I used the Gaussian filter. And for now, I just used the same X's for salt and Sleet, although in practice, they should be calculated differently. And then I'll just quickly show the results, but they are a bit underwhelming. So far, the difference is very small between the run without any parameterization and the runs with Sleet and salt. But maybe this is because we use a different way to parameterize the X's or need to include more. So yeah, I won't talk too much about that, and then I'll just sum up. So I've gone over how to apply these two methods to the primitive equations. So salt preserves circulation, and it gives a nice stochastic version of Craig-Leibovich. by modeling uncertainty in the transport velocity. And because of the way you do the Ito correction, you can you don't need to make this assumption about the X's being horizontal, so you can take into account the vertical variation more easily. Whereas SLEET has the property that preserves energy and models the uncertainty in the momentum, which makes it easier to configure the X's because you can take Eulerian differences. But in both cases, the effect is quite small so far, but I've only done a few preliminary runs, so it's perhaps not surprising that the results are not showing a huge impact so far. So SALT has a very slightly larger effect than SLEET from what I can see so far, but I didn't show this, but in the temperature, it can introduce some sort of artificial diffusion, which is another problem that needs to be dealt with. So more work is needed on how to configure the size. And then once that's done, I might need to consider ensemble runs to see if we can get, say, the true solution within the spread of the stochastic runs. So thank you all for listening.
Yeah, thank you very much, very much. That's an excellent talk. You did run out of time, but there's a break here until 2:10. If anyone has a burning question, Wavpan is asking a question. Go ahead, Wavpan.
Sorry if I missed it, but how do you compute V? Just from the equations, it seems that V is a free parameter.
Which equation, sorry?
The slide you had, this one. There's no equation for V.
For V?
Yeah, V. Oh, sorry.
Yeah. So V.
Yeah,
so V is the three-dimensional velocity. So the horizontal part is calculated by the momentum equation.
Okay, I see.
Yeah,
so in FLEET, then the circulation theorem, the loop is moving with just V.
Yeah. Mm-hmm.
Okay. But then that's not deterministic, right? Because it's part of it contains U, which is stochastic. It's just that you don't have the dW term in
Yes. Yeah. So it's not. Yeah, I guess it's indirectly stochastic because it's affected by V rather than V plus some stochastic terms.
Okay. Yeah. Thanks. Yeah, I got confused. Sorry. Yeah.
Mm-hmm.
Okay. Thanks again for all the speakers. Thank you very much for excellent talk. I really enjoyed this session. Let's meet again in 5 minutes at 2:10 and start the next session. Okay. The next speaker is Saeed Kuala, then Gilles Tissot, then Erwin Lisek, and Erlan Ponte. So is everyone here in the session? So Sayed, can you begin by sharing your screen? Okay, good. How are you doing? I don't hear you. Okay, I don't hear you. Not yet. I don't hear you.
Hello.
That's better. Now I can hear you. So yeah, but you're Gilles, right?
Yes.
So I can hear you, but I didn't hear Said.
Said, do you hear us?
We can't hear you.
No, we can't hear you yet, Said.
He says that he's gone to fix it in the chat.
What?
Said said in the chat, I will fix it. And he said, yes, I
Okay.
do hear you.
Okay, good. I should have looked in the chat. Okay, good. Good thing we had this break. So what a great session, huh? I really enjoyed that last one. Okay, Said, can you speak? Nothing yet. Yeah.
Hi.
Oh, is that you, Said?
Can you hear me?
We can hear you. It's maybe a bit low, but we can hear you.
Your ears are better than mine.
And now we
Oh,
don't hear you anymore.
Said, do you want to trade with Gilles? And Gilles, could you start and we'll let Said figure out this problem?
No problem.
Is that all right with you, Said?
Yeah, it's fine with me.
Ah,
Yeah, I could barely hear you.
hear you.
We heard you.
I mean, I have issues with my internet connection.
Okay, let's take it easy on Said. Let Gilles talk. Sorry. You can give the first talk, Said. I mean, Gilles.
Sorry, I didn't understand.
Gilles, you should start. You should give
Okay,
the first
no problem.
talk
I will
and
try to
take the pressure off of Said.
No, yeah, no problem. I will try to share the screen. Hop, partager le câble. Okay.
Mm-hmm.
And so you can see the slide.
Yep.
And it's switching.
Yep. It's working.
Perfect.
Go ahead.
Okay. So good afternoon. In this presentation, I will speak about stochastic linear modes in turbulent channel flow. So we'll focus on the channel flow, where you can see here two pictures of streamwise velocity. On the left, the flow is normal to the screen, and it is between two plates, and it's periodic in the streamwise and spinewise direction. On the right, you have a plan here that is close to the wall, and where we can see the presence of a structure quite elongated that is typical of wall-bodied flows and that we call streaks. And our objective is to develop some models that are able to predict these coherent structures. And we want to do this in the frequency domain, and we want to do frequency by frequency predictions. So once we have said that, we are facing a closure problem, and we will see how the stochastic models can help us for that. So the first idea we can have for predicting coherent structures in turbulent flows, it's to go towards linear stability analysis, where we start with the Navier-Stokes equations. We linearize over the mean flow. We assume that it's a steady state of the system, so this assumption can be discussed, of course. And we will search how a small perturbation will grow or decay in time. So we neglect the nonlinear term. And we perform normal mode ansatz. So we work in the Fourier domain. We do Fourier decomposition, Fourier transform in the spine-wise and stream-wise direction and in time. We introduce this in the linearized model, and when you obtain an equation for the u, v, and w velocity, for the momentum, and for the divergence-free condition. We introduce, written in a compact form, it has the shape of an eigenvalue problem, standard, where we search, we find the perturbation and we find at the same time the frequency, and it's complex, so it has a growth rate. The problem is that it doesn't really work well for turbulent flows because the nonlinear term is not small. So this is why there is a large research effort around what we call resolvent analysis. And the idea is the following. So we write the Navier-Stokes equations in the frequency and wave number domain. We put on the left-hand side all the linear terms, and so you can recognize here the eigenvalue problem that we have shown before, but we keep the nonlinear term on the right-hand side. Since it's quadratic, the Fourier transform of this nonlinear term is a convolution of all frequencies and wave number, and then it couples the frequency between them. So it's not something that you want to do. So what we do is that we extract this linear operator, and we will study it in terms of input-output, where the input is in terms of forcing and response to the forcing. So among all possible forcings, some are physical, so that they correspond to a real nonlinear term, and we have a physical response. The idea of resolvent analysis is to extract the most amplified forcings and the most receptive responses by studying this linear operator. So for that, we start with our nonlinear problem, and we replace the nonlinear term by forcing. Here we have a B matrix that restricts the space of the forcing we are searching for. So for us, we just restrict to the U component since it's a nonlinear term. And in the same way, we have a matrix H that is an output linear operator that restricts the output space. And this makes appear the resolvent operator, which is I minus I omega E minus 1. And by multiplying by H and B, we have this is called a transfer function operator. And the idea is to perform a singular value decomposition of this transfer function operator. So this is equivalent to maximize a Rayleigh quotient, which is maximizing the output for a given input amplitude. And in fact, performing the SVD, we extract two bases, two orthonormal bases, one of forcing, the V, and one of responses, with here, with the singular values, a diagonal matrix sigma of singular values that are the amplification gains. And for instance, if you take the first response mode, it is the response of the first forcing mode. They are associated one by one. Okay. So with this technique, we can have some discussions. In fact, the results of resolvent analysis will be exact compared to what we extract in the data if the forcing, the nonlinear term, acts as a Gaussian white noise. But of course, turbulence doesn't behave as such, and there is room for improvement doing that. More specifically, what we put on the left and right hand side of the equation, so in the linearized operator and on the forcing part, it's kind of arbitrary, and we have the possibility to introduce a part of modeling of the forcing in the linearized operator. That can be done, for instance, if we introduce an eddy viscosity. So this is today this is the state of the art of what is done with resolvent analysis. The idea is that it models the energy transfer at scales where there is high production. This models the energy transfers toward other scale by the dissipative mechanism. One advantage of that is that it's now adding an eddy viscosity, the mean flow becomes approximately the fixed point of the system, so it's center of the problem. But in fact, for resolvent analysis, it's not mandatory compared to stability analysis, where it's important. A big drawback of that is that it's purely dissipative. And especially if we have scales that receive energy from other scales, it will model it by a dissipative term, so it's not so good for this kind of scales. So this is why we want to improve this kind of modeling and use the stochastic modeling, the LU model, to improve this. So the idea is to decompose the velocity field in 3 components: the time average, and the fluctuation we split in 2 parts: a coherent part, our coherent structure, and a turbulent fluctuation that will be decorrelated. And these 3 velocity fields interact. The turbulent fluctuation is advected by the mean flow. It induces Reynolds stresses. The coherent structure is submitted to instability mechanisms by the mean flow. And what we want to add is the impact of the turbulence to the coherent structure by stochastic modeling. So for that, we use LU formalism. So I will go fast on this. Just principally, the idea is that in the resolved part, we consider that it is the mean flow plus the coherent structure, and sigma dBt will be the turbulent fluctuation assumed to be incoherent. So with this assumption, with the stochastic transport, when it's submitted to a stochastic transport, we have an additional stochastic diffusion, a drift velocity, stochastic diffusion, drift velocity, and the stochastic noise. And then if we apply this to the mass and momentum, we have the LU model. Right. So now what we want to do is that we will do the same step than in linear stability analysis, but we do this for the LU model. So we linearize over the mean flow. I have put in blue the terms of stochastic diffusion and drift, and the random terms in red. And we introduce a normal model and that we have to modify a little bit compared to the deterministic case. So we need a random perturbation of the phase for having consistent. And we add, we consider the Fourier decomposition of the noise. And then if we introduce this in the linearized system, we obtain 2 equations. One, which is a random part that with that we could predict the random phase, but in fact it involves the Fourier transform of a quadratic or bilinear term between. This is a transport of the coherent structure by sigma dBt. And this induces the random phase. But in fact, we will not use this equation because we are more interested in the two-point statistics. And then the second equation is very similar to the linear stability problem, where in blue we have some modification due to the stochastic diffusion to the drift, and for the random terms we have only one remaining, that is extraction of energy from the mean flow by the noise, and this acts as a forcing that has a structure of a stochastic transport. Written compactly, we can write it like this, where we have the modified linear system, and we can run an ensemble of these forcings and get the responses. And then we can compute the cross-spectral density matrix of the response, compute its eigenfunctions, and this will be consistent, comparable to what we can do in resolvent analysis, and comparable as well to STUOD. So STUOD are the eigenfunctions of the cross-spectral density matrix of the data. There is another ingredient that we had to incorporate. We will see later on the results, but we will need to introduce in some way interactions between coherent structures, the wave-wave interaction. And we need the Fourier transform of this term, and since it's as well a convolution over all frequencies and wave number, we model it just by an additive noise, and this will help for the prediction. We'll see this later. Another detail is that to define sigma, we need to ensure that the noise is decorrelated from the wave. And since everything is written in the Fourier domain, it is still harmonic, and but we will ensure the decorrelation between this term and the solution by doing this. So we take the cross-spectral density matrix, we compute its eigenfunction, and you say that the first one is our coherent wave, and the uncoherent parts, all the other modes from 2 to n, we will use this basis to define the noise, the Fourier transform of sigma dBt. So we do this iteratively, since we need the solution to define sigma dBt, so we do this iteratively, and in few iterations it converges. So this is what we get. So on top left we have what we have in the data. So this on the bottom you have the wall. The flow is normal to the screen, and the color are the streamwise velocity fluctuation of a wave. So we select a wave number and frequency that is typical of a strict structure. And so you see velocity perturbations in the streamwise direction, and you see streamwise vortices that induce a lift-up mechanism. We take low velocity from the bottom, we put it on the top, so it transports low momentum on the top and generates a low velocity streaks. And we take high velocity from the top towards the bottom, and it generates a high velocity streaks. Resolvent analysis gives what we have on the right, so it's interesting results. If we introduce AD viscosity, we have improvements. Okay, I didn't say, but we can have a phase variation, phase shift between the graph, but it's not important since it's eigenfunctions, and it's defined up to a constant and up to a phase as well. So we can have a shift in the spinewise direction. And on the right here, you have the stochastic model. So you see here that for the velocity streaks, so this is without the nonlinear forcing, and we see that we are able to reproduce pretty well the U component, but the vortices are not captured. The reason of that is that the lift-up mechanism is linear, and it's the stochastic model is able to, by stochastic transport, to transport this velocity. But the streamwise vortices are known to be induced by nonlinear mechanism. So this is why we have added the nonlinear force. and this is what we get. So we get a very good agreement with what we have in the data with this additional ingredient. If we look more quantitatively, so this is in Y, this is the wall normal distance, and I plot the U velocity in black of the data of the STUOD. The resultant is the red. Adding eddy viscosity, we have the orange, and the green is our model. So we have a very good agreement for the U velocity, and we have a nice improvement of the streamwise vortices. This is signed by the V and W components. So to conclude, here the stochastic modeling brought in this model the fact that the noise has a structure of stochastic transport. We have two mechanisms of stochastic diffusion and backscatter, and turbulence inhomogeneity is taken into account. We have checked that it's not negligible. And the stochastic transport is very good to predict the lift mechanism and then the Strix component. And for the longitudinal vortices, since we need wave-wave interaction, we were able to recover the right position, adding a small additive forcing. Thank you.
Yeah, thank you, Gio. There's still time for a couple of questions. Yuchan had a question. Paul was making a remark about it. And the question was about Lagrangian coherent structures, and they're asking about what are coherent structures. But maybe you could briefly say.
Yeah, so coherent structure, it's because we look at eigenfunctions of the cross-spectral density matrix. So we ensure that these modes are purely coherent in the sense that the coherence is one, so it's purely synchronized. We believe that it's a mathematical object that is physically relevant due to this synchronization.
Okay, thanks for the answer. So do you think there is a connection between the eigenfunctions in your case and the Kuma eigenfunctions?
So there are some paper making some this link, but they speak more about DMD than Koopman, in fact. But since it's
mathematically, do you think there is a connection?
For me, it's not 100% clear. But my feeling is that there may be a link since okay, it is in the Fourier domain, so it's in some papers they claim that, but strictly mathematically it's not. I think digging into this to make a strong link is interesting, because there should be one, since it's in the Fourier domain, and but it's purely coherent structure. So this is okay.
Okay, thank you.
Okay. I don't have a strong answer for that, but yeah, there are papers saying that.
Thanks already. Thank you.
Yes, thank you very much, Gio. Okay, it's been a good talk. So can we move on to our next speaker? Okay, so next we'll hear from Zaid, right? Are you ready, Zaid?
I mean, I'm ready, but I don't think that you are here.
The very low sound, very low. So you're going to have to really speak up. But I think it's very directional. I think you might find a direction where we can hear you. They turn to your right and see how things get. Now, talk on your right side. Say something. No. This is not fixed yet. Oh. I don't know what to do, Zaid. You want try various. I think it's your microphone. Do you have headphones or anything else you could use instead? So,
Hi.
Yes.
Can you hear me, Dail?
I hear you.
Oh, perfect. Finally.
What happened?
I have no idea, actually. I changed the PC and I changed the configuration. I mean, let's just do the presentation since it's working now.
All right. Shall we see if we can see your slides?
Okay, yeah, I will share my screen. 2 seconds. Up.
Yeah, big success. Okay.
Perfect. Yeah. Finally. So thank you, Gilles, for taking my place and giving me time to fix my internet issue. Hello, everybody. I will try to do a full screen mode. Yeah, perfect. Anyway, hello, everybody. I'm Saïd Wala. I'm currently a postdoc in IMT Atlantique and in Brest, France, and I'm going to talk to you today about the work we've been doing with my supervisors and my collaborators regarding data-driven dynamical embedding. Okay, the general context of this work is modeling ocean surface dynamics, mainly for forecasting and reconstruction applications. We are mainly interested in data-driven techniques, and one of the challenges of, at least in this presentation, I will focus on the fact that ocean surface observations are kind of a subset of much more higher dimensional governing system, and how to deal with this in a data-driven identification scenario. Okay. So in order to give a quick context of partially observed systems in context of ocean surface modeling, let's start with, for example, considering observations of sea surface temperature. They look like this. This should be a movie, actually, but I'm in my PDF, so you'll only see pictures. But they look like something like this. Is actually model simulations. It's not the raw ocean observations that may be coming from satellites, but the main goal, actually, of my work is to derive something like this model here that explains the temporal variability of ocean surface observations. In this example, we're taking sea surface temperature, but it can be sea surface height or sea level anomaly or other sea surface variables. But the main goal is to derive something like this differential equation that explains the temporal variability of our ocean surface observations. Now, the issue is the fact that in order to arrive this differential equation, this deterministic differential equation, we need to make sure initially that such a representation, such a deterministic representation can exist in the space of the observations, so in the space of sea surface observations. And in order to make sure that it exists, we need to make sure that our observations are have some properties with respect to the higher dimensional governing kind of dynamical system, which is the state of the ocean. Now, the state of the ocean is known to be governed by a partial differential equation that looks like this one. It includes various other variables that are in 3 dimensions. And going from this space of this partial differential equation to the space of observations can not be done in a way that preserves the deterministic properties of this model into the deterministic properties of what we want to build. Now, in order to write such kind of model that will be calibrated from data, we need first to make sure that our observation space is an imaging of the true state, of the state of the ocean. Now, from here, what we can do is we can do some synergy study or try to include other ocean observations that are somehow linked to our sea surface temperature and try to build a model from this. But if we do this, we will end up with the primitive equations of the ocean that we want to avoid. Another technique is to, instead of working on snapshots of observations, in order to define predictive models, so pretty much similarly to the model I just described in here, so predict xt at a certain time given an initial condition. What we want to do is, for example, predicting the ocean surface observations based on a dictionary of time series, of previous time series of ocean surface observations. This is known as take and delay imaging approach. But the issue is when taking such an approach is the fact that we need to define hyperparameters of this delay imaging, and doing it on a much high dimensional observations, sea surface observations is extremely difficult. We need to define some things like the dimension of the embedding and the lag of the embedding for every single point of the observations, and this can be quite challenging. Now, what we proposed is to treat this problem as an inversion of an augmented nonlinear dynamical system. We call this neural embedding of dynamical systems. And sorry for the busy slide, but it can be described in this figure. So starting from hidden dynamics that we do not know, we only assume that it exists and it is deterministic. Now, assume that we measure something from this high dimensional governing dynamical system. Now, these measurements are in our framework projected into a higher dimensional space. So here U, and we assume that this U is governed by a deterministic differential equation. Now, from here, what we do is that we initialize the initial conditions of what we do not observe of the latent states. So the Y's here, we initialize them as noise, and we optimize both the parameters of the data-driven model, so f theta, and the initial conditions, the Y's here, to minimize the forecast of what we measure, of our observations. So it can be written as an optimization problem like this one, and when we solve it numerically, we end up with a geometric reconstruction of the unseen phase space. This is pretty much what take and delay imaging does, but we also end up with a dynamical system, this f theta here, that can be used to forecast to advance in time the measurements on the observations. Okay, I will skip the example on the Lorentz, but we tried to apply this framework on sea level anomaly observations. This is not real observations, model simulations coming from the WMAP configuration. It's a ROM, a regional ocean model. It's called the Western Mediterranean Operational Forecasting System. It has a certain spatial and temporal resolution. So this is the resolution, the DT here. The temporal resolution is the resolution of the product. It's not the resolution of the simulation, of course. So it used this data to train our model using NeoF decomposition to reduce the dimension of the sea surface height measurements. And this should be a movie, but actually what happens is that we get a model that gives a pretty good short-term forecast up to 4-5 days, and that keeps simulating realistic spatial temporal structures that are present in the ROM model, in the regional ocean model configuration. Now, what happens is that after a couple of days, we blow up. The simulation blows up, and we notice that even in simple dynamical systems or in simple case studies, our simulation is just a chaotic transient of a divergent limit set. This is extremely bad because for example, in data simulation applications, if our analysis sends us somewhere here in the phase space, we directly make our model go to infinity, which also makes our data simulation routine diverge. We want to avoid this. So what we did is we included boundedness constraints to our data-driven model. It's based on the work of Schlegel et al. In 2013, where he proposed the generalization of the Dirac-Lyapunov method to include going from stability of equilibrium points to boundedness of linear quadratic models. And how we did this is based on this theorem of Schlegel. And how we did this was starting from the initial model formulation. What we do here is instead of a generic form for our model f theta, initially it was a generic form. It can be linear quadratic, it can be a neural network, it can be some kind of data-driven model with a basis function as long as it's differentiable to compute the optimization. We restrict to include the boundedness constraint for this model. We need to restrict the form of the model to be linear quadratic. So for this linear quadratic differential equation, we need to find a finite m, a finite point in the phase space. Around this point, the linear part of the linear quadratic dynamical system should have its eigenvalues, or the eigenvalues are its symmetric version. So A plus A transpose over 2 should have its eigenvalues all negative. And we also need to enforce energy preserving nonlinearities over the quadratic term. This is classic kind of constraints within linear quadratic reduced order models. But when enforcing these two constraints for a finite so shift in phase space, we guarantee that our data-driven model here is long-term bounded. So when it's long-term bounded, it means that if you pick up any initial condition, even if it's far away from the reconstructed trajectory, we still converge to it and we stay there to infinity. Okay, we'll skip experiments on Lorentz. So we also tried this on Lorentz 96, so the bounded version. And in Lorentz 96, for example, we assumed that, so we simulated the 40-dimensional Lorentz 96 system with this configuration, and we assume that we observe the first 20 variables and we never observe the remaining 20 variables. And when we apply our framework, we get both a good reproduction of the dynamics described, for example, in the power spectral density of the trajectories computed over long-term predictions, and a relatively good short-term forecast. It can be better, but I remind that we only observe the first 20 variables here. Okay, I will also talk about this case study and I will jump to perspectives, okay? This case study is on simulations of the shallow water equation. So we picked up shallow water equation with a given configuration. It's given here. So 1000 times 1000 kilometer domain with a given regularization, a given time step. And as training data, we pick the patch in the middle of the domain. So to simulate ocean surface observations with unknown boundary conditions. And we filtered this patch in the middle of the domain to kind of simulate unresolved scales. And we try to model this filtered patch. And hopefully this is a figure. So everything is in here. So when we compare our model, it's the first line here to other state-of-the-art techniques. What happens is that we get a good short-term forecast. It's in the blue panel here. It's not the best when compared, for example, to the Henkel EDMD technique, but when compared to Henkel EDMD, what we keep doing is we keep simulating realistic trajectories within the patch of shallow water equation after long simulation times, even without knowing the initial the boundary conditions or the unresolved scales. And this can be more described quantitatively through the power spectral density, both in time in left and in space in right, of the proposed model with respect to some state of the art. And what happened when we, for example, try to analyze the power spectral density, temporal power spectral density of the simulated trajectories with respect to the ground truth, is the fact that we are kind of enabled to recover the slow varying frequencies of the true model, but we do a good job in the mid and fast varying frequencies, time frequencies. And why, from my point of view, I think that this is due to our objective function that only includes short-term forecast cost with respect to the minimization of the error forecast of the observations, and those long varying frequencies are more revealed through longer simulations. So maybe we can get a better match in the time spectrum of the model by including an objective function that accounts for errors in the prediction up to a given time step that can be long. But this is an issue from a numerical point of view, so we still need to think about it, I think. Now, what is very good, on the other hand, is the match between the radially average power spectral density of the simulated field with respect to the ground truth. And what happens is that we perfectly match the ground truth spatial structures even for long-term simulation. This spectrum is averaged over like, I don't know, 10,000 simulations of the data-driven model, and it still matches the ground truth. Okay, I will not talk about the sea-level anomaly case study, but because you will not see the movie, but what happens here is that we are also able to get relevant models in modeling sea-level anomaly dynamics that are coming from a ROM configuration. So it's a toy case study. It includes only model simulations, but c'est encourageant. Okay, now regarding how much time do I still have, Daryl?
You have 1 minute before the question time starts.
Okay, 1 minute quickly regarding the perspectives. This is just kind of scientific curiosity from myself. I'm not talking much about it, but I'm wondering how to constrain the convergence properties of these dynamical systems to target a certain regime of limit sets. And this regime is chaos, and chaos is impossible to constrain by manipulating the dynamical equations. So I'm thinking about another way to constrain it without necessarily having to simulate long-time trajectories, stuff like that. And another perspective is regarding uncertainty quantification. Is in scope in the heart of STUOD, but what we are doing now to quantify the uncertainty of this kind of model is that we run several models for different initial conditions of the latent states. And when we train all of them, we end up with different models that, starting from the same initial condition, kind of give an ensemble of possible future state given the same initial condition. Now, this is a little bit expensive because you have to train lots of models, and we are kind of wondering how to explicitly include uncertainty into the proposed frameworks of going from ODEs to SDEs, and how to kind of the main challenge in here is how to parameterize the training of the diffusion term in order for it to be relevant and for the uncertainty to be truly meaningful. Another perspective is regarding closure modeling, but so we think that we can use some ideas of this work to target issues such as closure modeling, so including partial differential equation, and try to learn some terms in order to make these differential equations, these partial differential equations, explain the variability of some low resolution observations. And with this framework, with ideas, at least from this framework, we think that we can tackle the closure modeling problem without having any knowledge of the high resolution. So with only having low resolution, we can build or the closure terms that can be effective in forecasting and reconstruction application. This obviously comes with its own range of methodological and applicative questions. And we are trying to kind of define what should be the right thing to do within this perspective. The last one regarding integration schemes, I will not really talk much about it, and I will, if you want, I will, but I will let you give me questions. Thank you, Daryl. Thank you all. And sorry for the mess in the beginning.
No, that was a good talk. Very good. We have 3 minutes for questions.
Really?
And yeah, 3 minutes left for questions.
Perfect.
Yeah. So I don't have any questions. I think that somebody else should ask a question. You're outside my experience.
Oh, come on, you can get some experience in here.
I thought the talk was very imaginative. You know, he tried so many different directions. It's very creative.
Thank you.
So come on, somebody, Dan, are you there? You want to ask a question?
Can you hear me or?
Yes, I can, Paul.
Okay. I was wondering, in the beginning of your talk, you talked about a synergy study.
Yes.
Could you say a bit more about that?
I mean, what I mean about synergy study is kind of a legacy from what I learned in control when I was doing control studies. But initially, what you do when you try to build a differential equation to explain the variability of some observations, you try to look for what influences the variability of your observations. So you try to build a certain vector of state variables that are independent or generic enough to explain deterministically the variability of your observations. So in this context, since we know that at least we cannot build something like this directly for sea surface measurements, synergy study would account for example, including sea level height or sea surface salinity with your observation, and try to build a model with your state space not being only sea surface temperature, but sea surface temperature plus sea level anomaly plus sea surface salinity or stuff like that. So basically including other observations to try to model the ocean surface observations. This is extremely hard. And as I said, I think that it will pretty much send you back to your ocean primitive equations that we want to avoid, at least in this work.
Okay. I can ask more, but I want to leave if someone else wants to ask a question.
Okay, Saeed. Thank you very much.
Thank you. Thank you.
Okay, so could you stop sharing? So
okay.
Erwin can start.
Okay, can you see my screen?
Yes.
And can you hear me?
Yes.
And can you still see my screen?
Oh, no, I can't see anymore. No, I can see it.
Just to make sure. Okay, wonderful. Hi, everyone. Thank you for the opportunity to speak. I would like to also talk about thermal QG equations, but this time with boundary conditions. And this is collaboration with Daryl and Wei, but it's also Dan, Chrisan, Romeo, Laura, and Oana also have important contributions in all of the discussions. Can you see the Lofoten vortex?
Yes.
Wonderful. Okay, so one of the regions in the ocean where we think that the thermal quasi-geostrophic equations might be a very good model is the Lofoten vortex, which is a region of the ocean just north of the Faroe Islands and just west of Norway. And it's about a 500 kilometer radius, or well, 250 kilometer radius vortex. And this was a picture that Bertrand showed us. It was made on the 31st of May, 2020. Glob Current showed this ocean color data. So what you see in this picture is chlorophyll measurements. And this is this vortex is very sustained. It's present pretty much all of the time, and there's quite a few studies that have looked into the Lofoten vortex. one of the questions that we wanted to investigate is whether the thermal QG equations are actually a good model for this sort of vortex. But the thermal QG in terms of modeling is not the starting point. The starting point for ocean dynamics in principle for us is the rotating stratified Euler equations. However, these are way too expensive to solve numerically, and they come with $1 million open math problems. So you quickly have to abandon the rotating stratified Euler equations and transition into Euler-Boussinesq. But at the time where you're at Euler-Boussinesq, you're still in trouble because this is a model that you still struggle to solve. And then actually the next stage is pretty much the primitive equations, which, as we heard from Stuart, is the model, is the choice model for most of the ocean institutes. So for instance, MIT GCM uses these equations as well. A different route that you may take from the Euler-Boussinesq equations is by taking a vertical average immediately and assuming that the free surface waves are small enough, which brings us to the so-called thermal rotating Green-Nagdi equations. And what these are a simple extension of the thermal rotating shallow water equations, but these equations still contain non-hydrostatic pressure effects. So these equations have the additional benefit that the dispersion relation is much nicer than for the rotating shallow water equations. And what I mean by this is that as the wave number tends to infinity, the frequency for waves in thermal rotating Green-Nagdi saturates, whereas in thermal rotating shallow water, the frequency also tends to infinity. So these equations tend to make faster and faster and faster stuff, whereas for these equations, it tends to saturate. Then another simplification that you might do for the thermal rotating Green-Nagdi equations is the rigid lid limit. And this amounts to not allowing any free surface behavior. And that would bring us to the thermal rotating Great Lake equations. So the additional acronym, or the additional word here, great, indicates that there's still non-hydrostatic pressure effects present in this model. And then once you remove those, so similarly by putting a rigid lid on thermal rotating shallow water, you obtain the thermal rotating lake equations. And these are a quasi-incompressible, that is to say, weighted incompressible. These equations still know about the bathymetry, but it's a simpler 2D model. In addition, you can also go to one dimension. So in narrow channels, the 1D restriction of the thermal Green-Nagdi equation, so we ignore the effect of rotation in that situation, gives you Komassa-Holm type wave equations. If you do the same thing for thermal shallow water, you find the Saint-Venant equations, which are also still quite commonly used in modeling for all kinds of engineering applications. But the route I want to focus on is the asymptotic expansion of the thermal rotating shallow water equations around so-called thermal geostrophic balance. And this is valid when the Rossby number and the Fruit number are both small enough. And the first model that we would encounter along the way is thermal L1. So thermal Lagrangian 1 is the thermal extension of Rick Salmon's L1 model from 1985. And this model has quite some interesting mathematical properties that I don't want to go into in this talk. But if we go further and approximate further by requiring strict asymptotics, we find the thermal QG equations, which we've seen in Romeo's talk, are locally well posed. So also we know quite a bit about the structure of this set of equations. So we want to use this set of equations as a model for the Lofoten vortex that we saw in the previous slide. Okay, so let me just put the thermal quasi-geostrophic equation on the slide again. I write them in terms of stream function vorticity notation rather than velocity. In my case, Q is the potential vorticity. B bar is the vertically averaged buoyancy. So the bar indicates that this buoyancy still is allowed to vary in horizontal directions, but comes all the way from the rotating stratified Euler equations through vertical averaging. And H1 here is the bathymetry profile. In fact, it's the variation around a flat bathymetry profile. So this contains the gradients of the bathymetry. And F1 similarly is a departure from constant Coriolis force. So these two things are allowed to depend on space. Here we see the advection equation for potential vorticity. So it's being generated whenever the gradients of the bathymetry and the gradients of buoyancy do not align. Whenever that happens, vorticity is being generated, which is quite a violent effect, as we saw in Laura's talk. This term can destroy zonal jets if it's large enough. And the potential vorticity is related to the stream function via this Helmholtz equation right here. Now, usually in this picture that we have here, all of these boxes have in common that we derive them via variational principles. And variational principles, or equivalently Hamiltonian dynamics, is conservative. So all of these models are closed, which means that they can only deal with periodic boundary conditions or the boundary conditions that correspond to energy conservation. So these models are not allowed to communicate energetically with the outside, which means that in the picture of the Lofoten vortex, we would have to solve for the entire ocean to restrict our attention to this blob here. And we can't, for instance, draw a box around this and use inflow-outflow boundary conditions. So that's the extension I want to focus on in this talk. Okay, so first let us focus on the Hamiltonian formulation of QG, which is really useful because we will use this to extend to boundary conditions that are allowed to exchange energy with the outside. The Hamiltonian formulation for TQG starts with the following Hamiltonian, which involves the potential vorticity and the buoyancy as the two important variables. And given some functional f of q and the buoyancy, the equations of motion can be found through this Poisson bracket. And this Poisson bracket is quite special because it's a linear change of variables away from a standard Lie Poisson bracket, but it's not the standard Lie Poisson bracket. Now, another interesting fact about this thing is that it has the same Casimirs as the standard Lie Poisson bracket. So this model TQG, in fact, has an infinite number of conserved quantities that we can also, if we carefully treat the boundary conditions, also understand how the preservation of these additional conserved quantities changes. Now, in this formulation that we have here, because of the antisymmetry of the Poisson bracket with respect to the L2 pairing, the energy is conserved. So that is to say, if we put H in the place of F, then that would vanish because of the antisymmetry of the Poisson bracket. But in fact, this is only true if we have the boundary conditions that we saw on the previous slide. So these boundary conditions here in 2 are in fact necessary for this formulation to work in a Hamiltonian sense. So now we're going to step away from this and we're going to enter the realm of distributed parameter port Hamiltonian systems, which is a mouthful. Distributed parameter simply means that the parameters in the model are allowed to depend on space. So this is the partial differential equation setting for port Hamiltonian systems. And port Hamiltonian systems are very interesting because they allow individual components that can be modeled with a Hamiltonian system to communicate energetically with other systems. It comes from engineering systems theory, where, for instance, you have a flywheel and a harmonic oscillator that you would like to couple together, and you would like to exchange energy in such a way that the total energy of the combined system is conserved. And that's done here as well. So for instance, this top line is just saying that all the energy interactions that occur in the middle here balance each other out. And this structure that we see in the middle here is the so-called Stokes-Dirac structure. And this thing replaces the Poisson brackets that we saw on the previous slide. So this structure here is flexible enough to incorporate interactions through boundaries, interactions that dissipate energy, and interactions that involve forcing. So in the context of Stuart's talk earlier today, this port here, the external forces, that could be modeled with stochastically with SFLEET, and the interactions on this top line here from storage towards dissipation, that would be where salt lives. So additionally, port Hamiltonian systems could have a third model for noise, which could be through the boundary ports. And this is the sort of modeling idea that we're now going to apply to TQG systems. This plot here was made by Rami Rashad, who is a postdoc at the University of Twente, and he is doing fluid structure interactions with this sort of approach, which is also quite interesting. Okay, so let's first have a look at the energetic interactions through the boundaries. So now we no longer assume any boundary conditions. We simply see what sort of interactions the boundary can perform onto the Hamiltonian. So we take the Hamiltonian and differentiate it with respect to time, and then simply insert the equations of motion. After doing some manipulations that involve integration by parts, all of the terms that would be in the domain itself drop out due to the Hamiltonian formulation, and all that's left are the boundary conditions. And you can already see here that if you take the boundary conditions that we had before, the usual boundary conditions, then this term and that term, those two terms vanish identically, and you would have conservation of energy. Now, with any boundary conditions, this is the amount of energy that goes into the internal of the system. And we can do a similar trick for the Casimirs. The Casimirs are functionals of this form. They can be arbitrary functions of buoyancy, and one of these arbitrary functions is multiplied by the potential vorticity. And upon differentiating this with respect to time, we can do similar manipulations involving integration by parts to also obtain a formulation that only involves boundary terms. And these boundary terms also vanish identically if we assume the boundary conditions at the start. Now, if we don't, then this is the amount that the boundaries change the conservation of Casimirs. And so with the energetic and Casimir interaction of the boundaries, we actually know exactly what boundary conditions do to the internal system. So this way, we've now set up the information we need to set up the Stokes-Dirac structure that tells us how the internal dynamics changes depending on what happens at the boundary. And this is the formulation that would be required to isolate the Lofoten vortex and use inflow-outflow boundary conditions to model the internal dynamics for the Lofoten vortex. And how you isolate the Lofoten vortex is then up to you. So whatever happens where you can measure the inflow-outflow conditions the best could be used to select the boundary conditions. But I actually have quite a number of suggestions and maybe some discussion points that could be interesting in terms of how would we actually go about modeling an isolated version of the Lofoten vortex where we don't use a model for the full ocean. I mean, of course, we still need some model of the full ocean to even determine the boundaries, but we could isolate the TQG model and take observed data, for instance, along the edges. And one thing that might be useful for this is simply taking temperature and flow data from Glob current, which is continuously, well, pretty much continuously observing what's going on here. The data there is, I think, is really good. And another way of isolating the vortex might be through the bathymetry profile that we see in this picture. So I took the picture from the NOAA bathymetry data set. And this is the location of the Lofoten vortex. So here we see the Faroe Islands, here we see the coast of Norway. And it seems that the bathymetry really has an important role when it comes down to the Lofoten vortex, because Lofoten vortex is located in this area right here, which seems exactly in this deep part of this, in terms of this basin, this Norwegian, or I don't know if this is still called the Norwegian basin as well, but in this area, this is the area where the Lofoten vortex is situated. So perhaps this outline tells us what the boundary conditions could be, for instance, for an isolated model. So those are a couple suggestions that I just wanted to throw out. And I just want to mention again that this might be an interesting way, not just to model boundary conditions, but in principle model, use the Hamiltonian structure of many of the models that we saw in the picture earlier, and combine them with boundary conditions, and also think about what happens in terms of stochasticity. I mean, we're talking STUOD after all, and the S stands for stochastic. So we can introduce stochasticity in terms of the energy interactions that can amount to storage and dissipation of energy. So SALT modifies the Hamiltonian, and depending on whether that noisy part of the Hamiltonian is positive or negative, it does energy storage or energy dissipation. The stochastic forcing by Lie transport is a distributed port, and we could also have stochastic inflow-outflow boundary conditions. But in principle, all of these things start to interact as soon as we require that the total interaction is 0. So there's quite a few interesting modeling points of view that go into this framework. And with that, I would like to stop. I think it's a rather short talk, probably. I didn't go over time much, but hopefully you found it interesting. And if you have any questions, let me hear it.
There's still a couple of minutes left for questions if you have any. I think there's one in the chat. So, let's see. So is there a question for, is there a question for Erwan? So okay, so I have a question. The question I would ask is about where's the balance between the Eulerian and the Lagrangian boundaries? Okay, there's if you could you even have a boundary you wanted to adjust seasonally or something like that? Because you would like to have the simplest kind of boundary, and if you just choose a fixed boundary, then you have this formulation, but maybe part of the boundary could be fixed and part could be moving.
Yeah, so in principle, the modeling framework is quite flexible, but if the boundaries themselves are also evolving, then what I imagine anyways is that instead of really modeling this as a boundary port, I would have another model here that models what is going on with the boundaries here. So
yeah, so that would be a flux that would be the flux through the boundary then.
Yeah, exactly. Yeah, so the beauty of this framework is that these Dirac structures, as they're called, can be composed, and their composition still is a Dirac structure. And also, if you put convenient constraints in, or physical constraints, then the constraint Dirac structure is still a Dirac structure. So you can couple multiple of these systems together in a consistent way. And so, for instance, if you have a model for your boundaries and you couple that to the Tqg system, that can be done in a consistent way. So dynamically evolving boundaries can be taken into account as long as you have a model for that.
Great.
And
Okay,
as long as
thank
this
you.
model is in terms of energy. So all of these interactions are through energies. So the E's in this picture stand for efforts and the F stand for flows. So in fluid dynamical language, efforts are pressures and flows are flows. Or in electrical language, efforts are voltages and flows are currents. And their product, as you can see here, that's power, and power over time is energy. So that's that in this way, these systems are coupled together.
Power times time.
Yeah.
Okay.
Exactly. Yeah. Sorry.
So,
power times time. Yeah.
Yeah. Okay. Thank you, Erwin. Thanks for the wonderful talk. Yeah. Next speaker is Dr. Arion Ponte. I'm sorry for butchering your name.
No problem.
Are you ready?
Yes, I am ready.
Can you share your screen? And
okay, I'm gonna try to do that. Okay. Can you see my screen?
Yes, I see it.
Okay, let me try. I don't see my mouse. Okay, sorry. Okay. There we go. Okay, so thanks for giving me an opportunity to talk about our work here at IFREMER about high frequency motions in the ocean. And so I'm going to report more particularly today on progresses that we've made toward an experimental estimation of at least the magnitude of this type of motions. So I'm going to go quickly over some of the concepts here, because I think hopefully you remember typically this type of figure. So here we are looking at a wave number horizontally, frequency vertically, a diagram of representation of the surface kinetic energy in a numerical simulation, and we're focusing on let's call them small scale motions in the ocean. So we have a different kind of motions. We have first of all mesoscale ADs on the bottom left corner of the screen, so typical scales of the order of hundreds of kilometers horizontally, and time scales of typically months, week to months. And this is part of like a turbulent, let's say, cascade of energy. And we have smaller scale motions that are called sub-mesoscales that are associated with horizontal scales smaller than, let's say, tens of kilometers, and time scales of the order of a day to a week. And at higher frequencies, do you see my arrow when I move it? Probably not, right? No. Okay. So above the horizontal red line here on this slide represents the inertial frequency. And so it roughly distinguishes, like the lower frequency motions below these lines from the higher frequency motions, typically gravity waves and internal gravity waves more specifically. And so what's peculiar about so all of these motions is that they tend to occur on comparable spatial scales. And this is going to be, so there is a spatial scale overlap between these processes. And so it complicates in particular their separation in observations, and in particular for the future STUOD altimetric mission. One thing that is important to remember is that I think the one motivation behind our work is that there is overall little observations of whatever is above, let's say, the red line. And the goal of our work is to try to have more quantitative estimates about what's going on there. Typically, these are motions forced by tides, so perturbation of the ocean stratification produced by tides, or waves produced by winds. So typically, this would be motions that tend to be towards, like the near inertial frequency, so the red line. So motivation, as I said, like there is this satellite called STUOD that will be launched very soon in 2022. So it's the first of its kind, a wide source altimeter. So we will have kind of like for the first time 2D maps of sea level. And one thing that we could try to do with SWOT data is typically deduce surface currents by naively applying the geostrophic relationship, which is a balance between pressure gradient and the Coriolis force. And recently we were able to show with the postdocs that in many regions in the globe, so this is on the left side of this figure, the middle plot, whatever is red means large error. So if you take, your instantaneous maps of sea level and you apply geostrophy to predict currents, then you tend to have like a pretty large error if you're not in an energetic area of the ocean. And so we were able to show that high frequency motion, so whatever is above the red line on the previous slide, plays a big role in explaining these large errors. Another motivation behind our work is the emergence of high-resolution global numerical simulation of the oceans that start to resolve high-frequency motions like tides. So on here, for example, we're looking at the numerical simulations that we're using quite a bit in our group, so LSC 4320 numerical simulation. That's a horizontal resolution of 1 to 2 kilometers, and it's global, and it does resolve tide. So the one thing that is actually difficult to do with these numerical simulations is to know whether the high frequency variability that is now explicitly reproduced by this simulation is realistic. And so this is another strong motivation for our work. So we are very much interested by what surface drifters can tell us about this high frequency variability. What's nice about these surface drifters is that they provide now more and more observation at high temporal resolution. So that is hourly temporal resolution. There are about 1,500 drifters deployed at one given time, and this has been the case for decades. So there is quite a bit of data around. One thing that we've tried to do like a couple of years ago is that we estimated from the drifter tracks frequency spectra, and this is what you're seeing on this figure. So more precisely, we divided each drifter time series into blocks of times, of 60 days block of times, and we computed spectra along the trajectory over these 60 days time periods. And so the result is, for example, the gray line on the top right figure. And so one bold thing that we tried to do is we compared it with Eulerian frequency spectra from the numerical simulation. And so this would be the blue line, dark blue line on this plot. And so what our analysis indicated is that the simulation seemed to be deficient in near inertial energy, so that associated with wind by a factor of about 3. And that the simulation seems to predict more tidal energy that the drifters indicate by a factor of 4. And so we also observe some other discrepancies. So what was pretty striking, however, is that if you look at the global patterns of the banding integrated energy, so for example, here we have, so left is the numerical model, right is the drifters, and we have low frequency on top, near inertial frequency, semi-diurnal and diurnal. If you look left and right, you do see that the pattern seems to be all right, even so the magnitudes may be off. So this was a pretty interesting start, and so one blocking aspect, one thing that limited the impact of our study was the fact that there is potentially a bias between the Eulerian, let's say, diagnosed spectra on the Lagrangian one. Like the simple example is, if you think about, like that the trajectory on the right is induced by a mean flow, where this the time series of velocity along the drifter path would produce energy at non-zero frequency. Even so, the flow is perfectly steady. And so this is something that has been conceptualized, like in the past, and that we try to understand a little bit better in simplified settings. So here, for example, we focused on identifying such biases, Lagrangian versus Eulerian diagnostics, let's say, of an internal tide signal. So on the right, we are looking on top of an idealized basin. So it's forced with two types of processes, turbulent baroclinic, an unstable, baroclinic jet. The domain is zonally periodic. And the second forcing is that we're forcing with, in the south of the domain, a low mode internal tide, so low vertical mode. So it's a type of internal tide. So again, internal tide are perturbation of the oceanic stratification induced by the barotropic motions. And so, so here we are looking at the zonal velocity, and we are looking at it stroboscopically in order to get rid of, like the wave phase. So you do see the wave propagating initially at the, let me start from the start. So you do see early on, the wave propagating northward, and its propagation is affected by the turbulent jet. So what we did is we seeded such an idealized numerical simulation with surface drifters, and we compared Lagrangian and Eulerian diagnostics. So here, for example, we are looking at autocorrelations of the surface velocity at 3 locations, so in the north, in the top, in the center of the domain, and in the south. So let's look, for example, at the center. So if you look, what the internal tide produces is it produces periodic wiggles of the autocorrelation, and the rate of decay of these wiggles is associated with the incoherence or non-stationary, if you want, nature of the signal. So it's something that is fairly relevant for people interested in internal tide dynamics, for example. And so what you see left, there is a pretty big difference between the rate of decay on in the Lagrangian frame of reference, so along the drifter path, compared to the Eulerian one. There is a much faster decay of the wiggles in the Lagrange frame of reference compared to the Eulerian one. And so these differences, like so this corresponds to a broadening of the spectral peak in the Lagrangian frame of reference. And this broadening actually may have, like some impact on your ability to estimate the internal tide energy if you're analyzing Lagrangian data. So we rationalized this effect, and so basically what happens is that your low mode internal tide, there is no clear spatial scale separation between your internal tide and the low frequency flow, and so you cannot summarize the effect of the low frequency flow on the wave by an advection, a simple advection of the wave by the low frequency flow. And in particular, the flow as it manifests itself at the surface. So there is a distortion of the Eulerian wave signal in the Lagrangian frame of reference. And this explains, like what we saw on the autocovariances. So we designed a theoretical model in order to validate this interpretation. And we were able to verify, if you look here, we're looking on top, let's say, of our basin, and we're looking at the autocorrelation envelope of the fast signal. So lag is horizontal, and the meridional direction is on the y-axis. And so we were able to find a relationship between the Lagrangian autocorrelation envelope in the center and the Eulerian one. And so the prediction, for example, here is on the right. So we are able to reproduce this distortion of the Eulerian signal in the Lagrangian frame of reference. Okay, so let's move back now to the realistic configurations. So coming back to this business about estimating the high frequency energy from drifter tracks, what we did is that we seeded the numerical simulations that I talked about earlier, the realistic one, the global one, with surface drifters. And so we computed, like we did before, we divided, like the drifter tracks in segments of 60 days, and we computed spectra along these drifter on these blocks of times, and we compared what Eulerian, like spectra, and we compared Eulerian spectra and Lagrangian spectrum. So here, for example, I'm showing like the comparison between the globally average spectrum. And so you do see that there are some notable differences. So let's focus, for example, on the zoom in the bottom. So what you do see is that Lagrangian spectra tend to be wider, and so with a smaller, wider and with a smaller peak. So this is consistent again with a distortion of the spatial Eulerian spatial variability into temporal one. So an aliasing which widens the frequency peak. So we went further and we integrated the energies into bands. Oh, so sorry. Yeah, I'm going to skip that. So we went further and we integrated energy within frequency bands of interest. So here, for example, we are looking from top to bottom at the semi-diurnal, near inertial, and diurnal bands. And so what we found out is that there is indeed some sense, the bandwidth of integration is indeed important. You need to pay attention to it. For example, for semi-diurnal motion, you need to make sure that your bandwidth is wide enough in order to capture the variability. And because of the precise reasons that I've highlighted with the idealized numerical simulations. But overall, like the agreement between the Lagrangian derived spectra and the Eulerian one is fairly good. So, which is fairly significant results because it means that if you can rely on surface drifters in order to provide accurate information about high frequency motion, at least their magnitudes. So this is the main conclusion of the talk. And so another conclusion from this very last piece of work is that in our earlier comparison between the numerical simulation and the actual drifter trajectories, we can now with a fairly good confidence attribute the discrepancies that we observed to the lack of representativity of the model. We know, for example, actually that for forcings, for tidal motions were a little bit too strong. Dissipation of high frequency motion is probably also not accurate, and also, like temporal coverage of the model and that of the observation are not the same. So this could explain, some of the discrepancies that we were seeing. But the Eulerian Lagrangian buoyancies were most likely not responsible for these discrepancies. So future work. So now we are going to build upon these results in order to develop a climatology for high frequency motions. There are a couple of steps before going there. Most likely we'll have to address seasonality effects. Also, one question that we'll try to answer is to decide whether there is enough information in GDP, so the Global Drifter program data, in order to go to the wave number frequency description of the variability. And it's not clear that we can do so because it's going to depend on the drifter, the amount of data basically that we have. And with that, I'm going to thank you and take questions if you have any.
Thank you. It's a fabulous talk. Yeah, I don't see any questions in the chat, but please, let's have a question. Let me start by saying that I wonder, is it possible that sometimes you would have your Argo floats, for example, coordinated in some way, like in a slice, right? So that you can look at a vertical slice in different, say different latitudes and with some, not different latitudes, different levels, vertical levels, with some kind of horizontal correlation between them. Okay, because when you make this conclusion about the local spectra, there's a lot of other correlations you could put into place, right? So, do you do that type of stuff with? Do they do it with the Argo floats to coordinate them so you can see the correlated data?
I'm not sure I understand very precisely your question. Let's see. One issue that we have obviously with the Argo float is the fact that they have like a fairly poor resolution, temporal resolution compared to the processes that we are interested in. Now, if there were enough of them, we could probably try to extract information, high frequency information based on the correlations between what pairs of floats could measure. But I'm not sure there are really enough of them. One thing that I'm just going to mention for now is that there is in some of the Argo floats have been configured in order to measure during, like the way Argo floats work is that they sink to about 1,000 meters, and then they drift for 10 days, and then they dive deeper down and go back up to the surface. So during the drifting phase of these 10 days, some of the drifters are configured to measure temperature and pressure at like a fairly good temporal resolution. So let's say about an hour. So even if you don't know, precisely, the float position, like people have shown that you can see high frequency variability and presumably internal tide variability along, the drifter path, and this may be relevant to your question.
Yeah, I'm thinking that we have enough Argo floats. Maybe we can start thinking about a swarm of these Argo floats taking data and getting some kind of correlation.
Yeah.
And because then you'll have both spatial and spectral information.
Yeah. One thing that we have to keep in mind with Argo floats is that, as actually it will be the case for STUOD, like we have still like a fairly instantaneous measurement. So the high frequency variability is still there. It's just that, like it's our ability to easily extract this information that is challenged.
Yes, definitely challenged. I can't believe we're working on such a hard problem. Good thing there's so many of us. Okay. I want to thank all the speakers. Yeah, congratulations. These are great talks. I really enjoyed this. It's absolutely fabulous. Let's see, there's a couple more. Look in the So I will look in. Noah has a question for you too, I think. Oh, no, maybe not. Yeah, maybe so. Noah, do you want to talk, maybe make your comment out loud?
Yeah, yeah, it was just about the frequency band. What you mean about bandwidth here? So I guess that's just the frequency band, right? Like if you have a spectrum in Fourier, that's just the width of the band of frequency you're considering.
Yes, correct.
Cool.
May I ask a question, or is it too late?
Not too late.
Okay, thank you, Aurélien. I had one question. You showed us simulations of the real trajectories of floats of these drifters, across the whole entire oceans. But I was wondering, at some point you can see that there are some areas where there are not any Argo float left. What's the because these drifters, they have a limited lifetime, right? After some point, they just go into the deep ocean, and so what's the time scale? In the simulation, I don't know if my question is clear.
Yeah, I can provide some more elements for that. So very quickly. So first of all, these are not Argo floats. They are surfaced drifters. So they are constrained to the surface. And, they have a drag at 15 meters depth. And so they are presumably representative of the motions of the currents, at that depth. Even so, there are a good fraction of them have lost their drag. And so they are more affected, for example, by direct wind effects. The gaps that you're seeing here are actually, the results that I've shown are using another, let's say, Lagrangian simulation that is seeding, continuously the ocean with drifters. So in fact, we never allow, for these holes, like in the data. The numerical simulation is 1 year long, and so that's like we're limited, by basically the length of this numerical simulation. In reality, you're right. So these surface drifters have a limited lifespan of typically of a couple of years, and but a couple of years, if you're sampling at an hourly intervals, this is already quite a bit of data. And so actually the fact that the drifters are moving around and exploring the ocean, for us is an advantage if we want to, sample high frequency variability a little bit everywhere. But in reality, you're right that we tend to have less drifters in the exact same areas actually that are indicated here on these figures. And this is an ongoing effort by the people of the GDP program to, continuously seed the ocean, like in these areas.
Thank you.
Yeah, thank you, everybody. Thanks so much. See you guys tomorrow morning, bright and early. Okay. Bye-bye.
Said, are you still around? Because I wanted to ask you a question. Shall I call you later, or what shall I do? He's gone.
No, he still has a problem with his mic, I think.
Oh, I see. All right. Okay then.
But maybe you can send your question by email.
All right, I'll send him one. I mean, if he's coming on Monday, we can talk on Monday. But I'll send him a question by email.
Send him a question for that to prepare on Monday.
All right. Hi, Juana.
Hello.
That's what happens when you have two